So what we want to do is, it's been such an upswell of interest of getting involved, and so we try to create more opportunities for the different members to get involved, particularly with our multidisciplinary topical assemblies. So if there's something in here that you think that you might be interested in contributing on, please do reach out. We've also just started, this is really exciting, the first in history Masters of Tall Building and Vertical Urbanism. This is a collaboration between the Illinois Institute of Technology and the Ctbuh, and it's really the first advanced degree on what we think is really a specialist discipline. So I'd say check that out, it's really interesting. Also, again, just another plug, the new chapter in Southeast Asia. So do reach out and get involved. Now, without further ado, I'd like to welcome you to the Future City. And really, just a little frame what we'll be talking about here. I've got some starter slides. Now, I love this cartoon. I think it originally came out in The Guardian. Our whole lives have been dominated by COVID over the past couple of years, and still the effects are lingering on. But you can see here, by coming together, we've really made some headway and started to make progress against it. This is showing the world battling COVID. But I think what's interesting is you see they're just waiting on the sidelines. There's even bigger challenges for us that we need to start addressing. Today's topic will be talking about post-COVID, what are some of the things that will redefine vertical urbanism? And this other slide I think is also really interesting. You can see these tsunamis of challenges that are coming at us. We have the wave of COVID. Be sure to wash your hands and all will be well. We've definitely made progress there, but we've got others waiting for us to solve. And I'd love to hear our speakers weigh in on some of these other topics here today. Now, the Future City is actually a global conference that's already taken place over 19 plus cities. Some of them physical, some of them webinars like they are today. But it's been really great to see us change our program. I had a chance to actually participate in the London and the Copenhagen event. Really happy to be here with you today too. But it was so nice for people to get together again physically to be able to meet and discuss. And so far, the Future City conference has been over 1,000 delegates, 200 plus presenters in close to 20 cities with many amazing sponsors. So thank you to everyone who's been involved, and thanks again to the organizers today for making it happen. And also we want to thank our sponsors and also the organizers for today's event. So without further ado, I want to again welcome you from the Ctbuh Global and Southeast Asia to the Future City. Let's reach for the skies. Thanks, Nadia.
Great. Thank you, Sean. Great. So our first speaker today is a designated expert of tall building design for Ctbuh and technical director of Gensler. He is a licensed architect in the state of New York, a member of AIA and lead AP, responsible for technical leadership and design realization at Gensler San Jose office. So here, please welcome Peter Chu.
Thank you, Nadia, for the introduction. And thank you, Sean, for a great summary of Ctbuh. I started as a Ctbuh member a few years ago, and I really enjoyed the conferences and all the information. Makes me miss the face-to-face conferences even more. Can you see the screen?
Yes, looks great.
So today I'd like to kick off the presentation with a personal story. I joined Gensler in 2018 in the Shanghai office. For 3 years, I was the technical director for the tall building studio and worked on numerous tall buildings and super tall building projects in the country. Earlier this year, I transferred to San Jose, California, and there were a lot of changes architecturally, but also tall building wise. I felt like it was a big contrast, and just based on the height and size of the scale of the projects, felt like things were getting smaller. But I've learned and retaught myself that it's not just about the heights. And there are many things to consider when designing tall buildings, and the cities that they inhabit. So I'd like to talk about my journey and present some of the tall building projects designed by Gensler in the offices in China and US. Let's see. So as I said, recently moved from Shanghai to San Jose. Apologies to Alaska and Hawaii. I just kept the continental US for the nice contrast and balance. But you know, the two cities seem very different, but the more I studied and experienced, there are quite many things that are parallel to each other. So Shanghai is the biggest city in China. It's a global financial hub, and with over 24 million people, it is truly a megapolis, and the population density is 3,030 people per square kilometer. So it's by all means, it's a massive city. San Jose, with just over 1 million people, it's, you know, tiny compared to Shanghai, but still it's one of the biggest cities west of Chicago. It's the biggest city in Northern California and capital of Silicon Valley, where, you know, a lot of the technology headquarters are based. The population density is 2,000, almost 200 people per square kilometer. So it's, you know, nothing to sneeze at. And, you know, in a different way, a very dense, populous city. However, you know, when it comes to building height, of course, they couldn't be more different. Although there seem to be more similarities now. San Jose is very unique. The international airport is nearby downtown, and that automatically means the maximum height cannot intrude in the flight path. So depending on the zone, buildings can only be 35 feet tall, which is 11 meters, to 390 feet. And in nowhere in the city can there be buildings taller than 400 feet, which is 122 meters. So compared to that to Shanghai, where until 2019 there were no height limits, Shanghai Tower, designed by Gensler, is currently at 632 meters. So that's a massive tower. However, in 2020, the Chinese government realized that there was just too much competition with building taller, and announced there will no longer be buildings allowed to be, you know, 500 meters or taller. And earlier this year, there are more detailed regulations, and now cities with less than 3 million people cannot build taller than 150 meters. And in general, taller than 250 meters is banned, and only cities or projects with special government approvals can go beyond 250. So 150 meter limit and the 122 meter limit in San Jose now are quite close. And I think this shows that, you know, we cannot only focus, and this is a maximum building height map of San Jose. The red dot shows where the Gensler office is downtown, and the airport is just off the map to the north. So as you get further away from the airport, you can see the numbers increasing, but still nowhere in the flight path. 390 is the maximum, and 400 is the maximum height in this region. So all this shows that, you know, as supporters and fans of tall buildings, you know, as designers and developers of this building typology, you know, we get fascinated with the height and features and you know, the facade design and things like this. But, you know, ultimately, the tall building is to bring density and people into the city. And we have to remember that we want to bring positive impact to urbanization, and that all this is to create a healthier and more sustainable city for the region and for the people living inside. And the taller we build, the technical challenges become greater, and this requires a additional amount of resources and investment. So really, why we want to build tall and how we can build the best tall building, I think that is a question, just that we have to remind ourselves and remember. And I think it's easy to overlook these from time to time. And that's why I think it's really great that Ctbuh not only has the TB, the tall building, in the name, but also the UH, the urban habitat, and just just reminds us that this is what tall buildings are about. So in the next few slides, I'd like to show a range of tall buildings designed by Gensler, but they all, we try to focus on bringing nature, sustainability, and the human scale to these projects in different ways. The first project is Zhongnan Center. This is the last project I worked on in the Shanghai office. It is 499 meters tall, so just under the 500-meter limit. It is currently under construction. It is near a grand lake and has access to the parks, the canals, and is on axis with the old city and the new city. So it's in a very prominent and beautiful site. As many developers do, same in China and in the US, the client wanted to really maximize the floor plate, make sure every square meter was utilized. So this building, unlike other super tall towers, really stays straight. It tapers very minimally, and this created a big challenge, not only architecturally for the massing, but structurally because of the wind loads and the core design. So first of all, we try to taper the tower as much as possible, and then we cut the corners to reduce the wind load and disperse the wind path, and still fill with another layer of interior spaces. So we keep the area, but sculpt the exterior so it visually looks less bulky, but also works for us structurally. The biggest highlight and most interesting part of this tower is that it has 7 interior atrium spaces. So it's a mixed-use tower with office, hotel, apartments, service apartments, and observation. And in order to maintain a livable and a unique residential space, the client really wanted to have these interior courtyards. So mimic outdoor courtyards would bring him into this tall building, which really hasn't been done before. I can only imagine Jinmao Tower, but that's a hotel, and at the very top with different conditions. So this was one of our biggest challenges, and this really inverts the core design. So rather than the central core getting smaller from the outside as the building goes up, this one, the outer face of the core stays the same, and it becomes hollower and hollower. So we make the atrium bigger and bigger as the building goes up. This creates a very interesting space, but also creates a problem. How do you make this space habitable, humane? And we had to integrate technology in order to resolve this challenge. So to bring natural light, daylight, and to make a more healthier space, we integrated fiber optic cables. Now there are new technology where there's solar collectors on the roof which follows the path of the sun, and you can bring daylight into these deep spaces. Not only is this better for people psychologically by feeling connected to the outside, but also it brings the full spectrum of light indoors. So you can grow a wider range of plant species and trees. Also, to improve the interior condition, we supply fresh air from the bottom. So it has an underfloor air supply system, and the exhaust is at the top. So this creates a natural flow of air, and also minimizes the volume of space we need to condition. So it's more efficient and also healthier and more comfortable for the people inside. And at the top of the building, we have an observation deck with a tune mesh damper on display. And again, we try to really maximize the view, also bring daylight into the building. So in the center of the crown, where above the TMD, we have these skylights where daylight is brought into the building, where you can see the sky from the center and view the lake with 360-degree views. So this is the view of the crown, where we really tried to maximize transparency, connection to the outside, and views to the surrounding site. Next project is another 500-meter tower in Fuzhou, and this one tried to bring nature into the tower in a different way. This also is a very complex mixed-use tower, and as most of you know, a single-use tower is really not practical nowadays with the sheer height and amount of floor area. But also, in order to make this economically viable and a 24-hour building, the client and the developers really tried to mix program, and the residential part is key, because they can sell the units, but also it makes the building alive and functioning throughout the day and the year. Where the previous tower had the residential up in the top zones, this tower actually has them on the bottom portion, and this was due to a regional regulation where apartment buildings cannot be taller than 150 meters. And the government said, although this is a 500-meter tower, the apartments cannot exceed 150. So we had this unique situation where the floor plates are the biggest. We have the residential spaces, and the offices above occupied the smaller floor plates. Through various studies, we tried to understand, I'll skip some of these images, how to make use of these large floor plates. And eventually, we have carved out the main area facing the ocean, and create this large atrium space within the residential zones. So if the previous project had the atrium in the center of the core, now we have a atrium facing one side, and this is the southern side of the tower. So this is a little bit similar to the Shanghai Tower diagram, where we have a sky garden within the tall building atrium. But what's different is the outer layer here is much more permeable with operable facade which allows natural air and light to come in. So this is a semi-indoor-outdoor space. So you have the benefit of not leaving the building directly outside your apartment. You have this indoor garden or park at every 10 floors. So this and also creates a buffer from the southern sunlight in the summer and can become a solar collection space during the winter times. So these are two different ways we try to bring nature and a more park-like outdoor space into these tall buildings for a 500-meter tower. Next project, I will introduce 3 different towers in downtown San Jose, which Gensler is currently designing or are under construction. The first one, the first tower, all of these are similar in height, as I explained. They're just under 400 feet tall. And the first tower introduces sky gardens in the sky, similar to the previous. This is a 3D map of downtown San Jose. The current tower is in the orange, and the other dotted buildings are all designed by Gensler. And we are really trying to introduce this hybrid tall building typology where we are creating these more massive floor plates, but carved and cut to create a more human scale space on the ground, but also bring in daylight and air into these deep floor plates. Again, similar to the first tower I showed, the developers are really trying to maximize the efficiency, which is part of the reason that the massive floor plate design is happening. Also, because of the technology companies' request to have these large flexible floor plates where they can lay out different programs, shift the interior layout if needed, and also promote communication and more interaction between teams and groups. So the floor plates are getting bigger, and interior connections with stairs and other visual connections become more important. The red dot again is the location of Gensler's office, just to give you a feeling of downtown San Jose and where we are located. So here we started with the maximum buildable envelope, and then studied the views and spaces where it would be best to create these outdoor terraces to have views and outdoor spaces where people can enjoy. So towards the internal side of the block, we have flexible working spaces, and towards the outer side, the main street and corners, we create these micro terraces and macro terraces where people can enjoy the outdoors and take a break from work, but also integrate and socialize for collaboration, recreation, and even dining. Also, we've done extensive solar studies to understand what type of sun shading we could introduce to the building. So the north, east, and west sides, we have added vertical louvers to reduce glare, but still provide views to the outside. But the southern side, we have added horizontal louvers. So we are customizing the facade details depending on the solar condition and orientation. This project is another project near inside downtown San Jose, and we have a similar idea of creating these outdoor balconies. We've called them bridges in this case, and again, the block is a massive block with 80-foot deep floor plates from the core. So they're almost 25 meters deep, which is you know, more than 1.5 of a typical office lease space. However, we've carved these light wells or canyons so daylight can penetrate deep into the space and naturally create these outdoor break spaces within the space. So here at the lower level, lower left, you can see our solar analysis. By creating these canyons, daylight can come in much deeper into the office floor plates and creates these pockets of indoor-outdoor spaces. There are some views, and this building is currently under construction. And the building you see beyond is the last project I will show you, which is San Jose's largest development in recent years. Here again, it's a great site directly next to a city park, and this project again tries to take advantage of the large city block that it's occupying, and we have created these 3 broken blocks connected by sky bridges. So the ground level, the paths are connected with the existing streets and alleys to bring people in, but then we carve away spaces to create natural entrances and resting spaces. So the park system can is brought into the block and then also brought up into the upper levels through the bridges and the roof garden. So we are trying to connect to the human scale on the ground, and then with the people and workers on the upper levels. The height of these towers are about 110 to 120 meters. And if you compare the dimension with a 300-meter tower that I worked on in Shanghai, it's actually quite comparable to cutting this 300-meter tower into 3 blocks and connecting them with bridges. So on the left, where we try to integrate these outdoor spaces on the face of the tower, we're able to do the same with these sky bridges and at the ground level parks connected to the city park. So that's the conclusion of my presentation. Once again, this journey has reminded me that that tall buildings are for the people and for the city, and it's the urban condition and urban habitat that we are trying to improve. And the tall buildings are not objects on themselves, but part of the urban environment. Thank you.
Thank you, Peter. Peter will now select a few questions from the Q&A box.
Okay. Okay, the first question, at every floor lobby of tall buildings in China, is there any mimic panel? That question just got deleted. I'll read. Do you have a mimic panel at every floor lobby? I'm not sure what the wording means. Does any of the other panelists understand this question? Mimic panel at every.
Peter, you need to click on publish to see all the questions.
It says, okay. I'm not understanding the question, I apologize. If somebody can check what the Mimic panel is, I will try to answer. I will go on to the next one. Is there a difference between building design process in China and US based on your experience and observation? Great question. So in general, every project is unique, which kind of makes them all the same. But what is most unique about designing in China is that international firms can only design up to DD stage, and the construction documents are taken over by the local design institute. So this allows us to work on more projects in the same amount of time, but also creates this gap between the end of DD and the beginning of a construction. In the US, most of projects we try to carry through construction document phase, and there's less, it's more of a seamless process, but it takes longer, and you work on fewer projects. So I think that would be one of the big differences. Do you think cities and tall buildings are less important now since many people are working from home after the pandemic? Great question. I don't think so. And as Sean talked about in the beginning, in 2020, there was a lot of fear and concern of the role of tall buildings and cities. But as we've seen now in 2021, many countries are back to normal, and developers are really trying to take advantage of this time and build quickly now. Also, based on Gensler does many research projects, and we have been interviewing and surveying many of our clients and developers, and they say many leading high-tech companies and leading companies are planning to actually increase their offices and expect people to live and work in cities the more, if not the same. And definitely there will be a more hybrid and different type of working and living situation, but definitely don't think that the importance is going down. Okay.
Thank you, Peter.
Thank you very much.
So our next speaker has been working with Arup since 1992. He was the first global leader for Arup Tall Building Skills Network and served as the regional Seismic Skills Network. He is currently the leader of the Regional Structural Skills Network and Modular Construction. He has published more than 40 technical papers in international journal papers and conferences. Here to discuss the important elements for tall buildings, please welcome Dr. Gorman Ho.
Hi, thank you. Thank you for your introduction. And let me share my screen. Hang on. You see the full screen?
Yes, looks great.
Okay, thank you. Good morning, everybody. And my name is Gorman Ho. I'm based in Hong Kong. I've been working in a number of tall building projects in the region. Although majority are in China, but I do have others in Ho Chi Minh City and Hanoi and Manila and so forth. And I'm going to share with you and similar to what Peter generally, but not exactly. And after 9 kilometers, I built more than 9 kilometers of tall buildings so far, and with the tallest one with 600 meters. And I'll see that, as a structural engineer, what we should look at and also, you know, for tall building, or how the tall building is actually impact to a city, and what is the benefit, etc. I think I'm not going through a single project, but I would like to share my view on tall buildings, you know, and I think I'm born in Hong Kong, and also, I mean, you can see this is a photo of Hong Kong, Victoria Harbour, and in 1960s. And you will see that at that time, I think is probably after the war, about 15 years, 20 years, and the society and city is going to be very stable. And also the economic is also going to grow. And once you got a city have an economic growth, the population will also grow. And you will see that in after 10 years, you know, Hong Kong has made a rapid change, and you will see quite a number of tall building is being built, and especially in the harbour side, and because this is firstly, we see that the fat land, you know, the land is fat, and at the same time is our central business district. And also you see that because the view and so forth, people would like to have tall building, looking at the harbour, etc. And then after like another 20, 30 years later, this is how the Hong Kong looked like in 2017. And you will see the more and more tall building is going built, and with the IFC2 here, it's the IFC2 380 meter, and Cheung Kong Center 300 meter, and ICC, which is about 460 meter, etc., etc. You know, is building along the harbourfront, right? And this make Hong Kong with a very special, you know, a new skyline, right? And you can see that the IC 400 and something, and then there's a K11, and also the New World Plaza. You know, all these are the new skyline when you you know, from the Hong Kong Island, you look at the Kowloon Peninsula side. So you change the skyline, right? What is called the new skyline for Hong Kong? And I mean, sooner or later there will be all others, you know, coming up on the other side as well. I think Hong Kong is probably like I would say Hong Kong is like a catalyst, right, to a lot of Asian city. And with this model, and it applied to been affecting other cities as well. This is the photo in Shanghai for Shanghai Pudong area in 90s. But you will see that the also have a very similar to Hong Kong, but this is what we call the harbor, but it's actually a river. And this is the really old Shanghai Bund, right? And here is the Pudong area. But it's the same with the open and reform policy of China in 80s. After 10 years, I mean, the Shanghai can make a lot of change as well. And also from that, you will see that in year 2010, right, in 20 years, this is how the Pudong looks like. And I mean, Peter, I just mentioned about the Shanghai Tower there, but it's under construction. So you see, you know, with, you know, this kind of period in and so on, you see the whole Pudong area change rapidly, and to be like a modern city metropolitan. At the same time, the population of Shanghai was increased from 90s is about probably less than 10 million people, and now we have a 26 million to 28 million population for the whole Shanghai. Right now, do remember it's just part of Shanghai. Pudong is part of Shanghai. We have all other area in Shanghai that's also under developing as well. And you can see that, you know, this new skyline has been changed, you know, and make another remarkable a journey for the city and also to the world too. And similarly, this is another one in Beijing, and which I personally have been working in Beijing for 10 years, from year 2000 to year 2012, before I returned back to the headquarters in Asia. And you can see that, I remember when I first arrived Beijing, I'm doing a building which is only like 150 meter tall, and that time is already, say, the tallest building in Beijing. And afterward, and I built this 300 meter tall China World Trade Center. And later on, we have the CCTV, and then we have the China June, which is 426, and then we have another China World Tower, phase 2, etc. Well, you will see that, the skyline of Beijing, the new CBD, Qiuyuan district on the east side of Beijing, the skyline has been changed rapidly in the past 10 years or so, right? Past 20 years or so, right? From what we call, every time I'm probably, sorry, I can't say, I'm beating myself. Yes, I mean, I built the tallest building in Beijing, and then after a year, another tallest building in Beijing, and after a year, another tallest building in Beijing, etc., etc. So it seems that the race has never ended. And but with the development, you will see that the city has also changed to another metropolitan. And I remember when I arrived Beijing in probably year 2000, I mean, the population is about 10 million. And by the time I returned to the EA headquarters, and the population is 26 million, right? So the city have been grown by about like 16 million population, in probably 10 years old. So that means that every year it got, a million population increase. So it's a huge amount. And that's why, I mean, the city, how to house or how to provide jobs for the people, and stack among the people, then we have to go for a vertical city. Similarly, I mean, besides Beijing, and you see that like Shenzhen, just our next door in Hong Kong. I mean, the building are also going very tall, and with the development, also the economic, I mean, the building also changed in terms of form and in terms of the function, etc. The one here is the Kinky Tower, and it got a hotel and also an office and observation deck on the top. And this is the Shenzhen Stock Exchange Center, and this is the office, and this is the trading floor, right? And also another one by Big in Shenzhen. And you will see that the building not, also you see that all the whole building has its own language or its character. I would say that besides China, I think other like Southeast Asia country have the similar development too. And they have like the in Vietnam and a couple of tall building, and a couple of years ago, and we just finished the landmark 81 in the Ho Chi Minh City. And you will see that, all these cities are getting to have a high rise and also getting tall as well. So we will see that, then we will ask a question, what's meaning of a skyscraper in a city, right? What's the meaning? Why we have to go for tall building? And why is that? I mean, of course, I mean, some people will say that it's a symbol of money, power, or economic. I quite agree with it. But at the same time, or maybe because of the city density. And city density is also, you see that the city density is also a function of the income of people. That means that if you go to the city, the more density, more density of a city is going to have, is supposed the income of the people in the city are more. in compare with like the urban or suburban area. You look at Tokyo, London, New York, Hong Kong, also. I think probably you will see this function. Or probably maybe some of the country or city, they want to say, oh, I want to have a flag, right, in the world. Or at the same time, I will see that when you look at the building, then it will remind the people that this is a building in which city or country, right? So this is, I would see that I think it's probably lots of cities would like to do so, right? Because they want to increase their tourism, etc., etc. And this is why I say that, you know, every city, I think I do agree that every city should have its identity, or I could call it a light of a city, right? So when you look at the building, then you will see, this is what city. You will look at ICC, this is Hong Kong. Or you look at the, like the China Jin, the CITIC Tower, I know, this is Beijing, or Shanghai Tower, this is Shanghai, etc., etc. But at the same time, you look like that, you know, what is meant by the tallest, right? What's meant by the tallest? I put two buildings here, and this is the tallest building in the world, right? And another one is going to be built. And in terms of height, right, this is the topmost height is 829 and so on. And the other one, which I designed, is about 597. Wow, in terms of height, you may say, wow, it's another, 200 meters less. Now, but you look at the data, right, you talk about the height where people can reach, right? This is the height of people can reach is 601, which is not, only 2 meter, 4 meter higher, right? Or high occupier is going to be 584. But for this one, the high occupier is probably 584 too, right? So it's pretty similar. And also you look at the GFA for this building is about 300,000 square meters, where this one is 370,000 square meters. Now you will see that, the functional building, or whether the ambitions of the developer want to go higher or they want to fully utilize the area, right? This is another thing that we should look at. And what's the mean by the best of tall building, right? Everyone may have their own definition, right? Whether you want to be in shape or you want to be in form, or so, right? And when Koolhaas, right, he said that instead of competing in the hopeless race of ultimate heights, right, dominate of the skyline can be achieved by a short period of time, or sooner or another. That means that basically you say, wow, this is the tallest building. From what he means is probably the life is very short, right? Because another challenge will come, another challenge will come, and another challenge is come. And that's why when he created the CCTV, and he have a different way of looking at it. But at the same time, or by means of this artistic, right, which is a very special form or so, or make it to be very spectacular, right? And this is probably a way maybe a lot of architect and developer are looking for. But also, I think by means of whether you match with the environment, this is a building in Taipei, in Taiwan by Big, and it make a building look like a mountains, right? Which is actually like a landscape. And we also use this landscape to we do a lot of calculation to make it environmental friendly, to reduce the heat in the podium. So people living there should be look like living in the countryside rather than in a city, right? This is a way that as an engineer we can help, right, to make our environment to be better. Of course, I mean, sometimes people will say, wow, uniqueness, right? Whether uniqueness is one thing, right? For CCTV, the area is, the CCTV building standalone is 450,000 square meters. even taller than the one I mentioned for 500, right? So 450,000 square meter means that it could basically, the whole development could be two, right? 600 meter tall tower. And so, but he don't want to make twin tower, and he want to make a unique feature. And because of the people in the tower, they need to communicate with each other very often, right? Because there are a lot of departments and so forth and so on. So they make a link. They make the top part to be linked with people, so that they will go for meeting at that height instead of going down and go to another tower and so forth and so on. So what we did is we make this very creative pattern by calculating which part is the with the highest force and which part is not, and then the area where have high force we put more member, and the area with less force we remove the member. So the actual pattern is telling you how the structural behavior, right? I mean, it's a good language for that because it's a TV tower, right? This is a broadcasting company. It's telling you, hey, this is how I behave, right? And so this unique pattern, but this form also create a lot of challenge to us as a structural engineer is how it's going to be built. And we in the design, we have already considered a couple of ways of doing it. And this is, we are fortunate that, the contractor come up with the one that we like the most. And also it's the one with the most challenge. And it link up, and then with all the tolerance within our prediction. So in the elements of a skyscraper, probably be function, right? And also of course, we need to consider sustainability. Of course, we also need to consider uniqueness, right? And all these, right, we also need to consider the energy efficient, the artistic, iconic, technology, and time. And technology or time, sometimes for engineer is important because we are limited at the moment. Usually our technology are limited to like a concrete and steel reinforcement, right, or steel. And whether we can go for even higher strength of concrete or higher strength of steel, it all affect our limit our sometimes I'll call it creativity or our innovation. But so because of this material, etc., what we can do is to have an innovative mindset to solve the problem by creating, according to different heights of building and also the form of the building, we create different structural system to suit, right? Now, there is no perfect structural system, right? Every building, because of its uniqueness, because of its geometry, we have to design to suit. And sometimes we will create a new system in order to suit. And you go for like a bit low, right? A bit low rise in, my definition of low rise is like 150 meter, and up to super high rise will be 600 meter, etc. All come with a different form, different structural form, different lateral system. But of course, it's not that as well, because now, architect, they have a new idea, a very contemporary art concept requirement. So we have to find a new way of solving the problem. In order to solve the problem, we have our own, like this artificial intelligence system that will fit the whether whether we should use some chip-in-chip system or mega brace system or outrigger system and so forth and so on. We will have our own, help to help the engineer to decide what's the best and so forth. It may also to meet your function of the building, whether it's an office, it's a residential, and so forth and so on. And for BIM, people may say, yeah, we use a lot of BIM. So what is next? And the next is we have our own smart AI console now for building. With the BIM, we can also put lots of sensor and so forth, so that we can capture the behavior of the structure from day to day, from week to week, from year to year, and so that we can calculate what is the energy consumption, how we can also improve it, or which season and we need more energy, or which season we can have less energy, etc., and so forth and so on. So it looks like a people, okay? So I will see that, a lot of city, we have a light in Chongqing, we have this Raffles City, and Guangzhou, we have the Guangzhou Sightseeing Tower in Thailand, also in Vietnam, and also in even in Cambodia. So I will say that, again, whether your city would like to have a light, right, and to show that your existence and also to the world that you are a great city. Thank you.
Thank you, Dr. Goman. I have someone texted me and asked, you've had a lot of experience with tall buildings. Which of these is your favorite and why?
My favorite, I think, will be I will always say that the next one.
Take your time.
Yeah, and I would see that why is so is the experience is accumulate, and every project has its uniqueness. As I said, they're different, and how we can come together all the experience and then load it into the new one, and then you add to one, right? So the next one would definitely be better than the previous one, right? And this is a challenge, right? And this is why I always talk to the young people to be innovative, to improve, to ask ourselves, right? How can you make it better, right? So my favorite project will always be the next one.
Thank you so much. We will be our next speaker. Thank you so much, Dr. Goman Ho.
Yeah.
So our next speaker is a regional director of Meinhardt Facade Technology Malaysia. With more than 25 years of construction experience, he had gained a comprehensive set of management and design skills, enabling him to find practical solutions to the most challenging of situations. Here to present 2 case studies on wind pressure management within tall building facade design, please welcome Nikki Hayes.
Hi, can you hear me okay? Hopefully the microphone is clear.
Yes, Nikki, can hear you clearly.
Very good, very good. Well, thank you to everybody that's joined the session today, much appreciated. And thank you to the other speakers. My presentation is going to be rather specific. It's to do with pressure on facades and how that that adjusts or changes as the building gets higher and how it affects tall buildings. And it's called Under Pressure. I thought of singing the title, and then I think good taste got the better of me, and there'll be no singing in the presentation today. Before I talk about presentation in general, I'd like to give a thank you to our collaborating partner TPP, who assisted with the wind loading presentation material. So over the years, Meinhardt have worked with various wind engineering teams, and we've had a lot of positive experiences. We've particularly enjoyed a strong synergy and a cooperation that TPP have provided to us. We've undertaken studies with them that go beyond what's typically performed through such collaborations. And our second case study today will demonstrate what we've been able to achieve by quantifying the results of these studies in terms of savings for a project or scheme. So this first slide here is an introduction to CPP, and then there's a web address at the bottom there, so you can check them out and see what they do at a later date. So today we're going to look at 2 case studies which will demonstrate how external or wind pressures can affect facades and why these require careful consideration and study, especially as buildings become taller and wind pressures increase proportionately. The first case study is Ilham Baru Tower in KL. We'll look at the facade scheme in general and showcase the system and material selection. After this, we're going to take a look at the various pressure studies that were undertaken, why they were required and what was achieved. And then the second case study, we're going to address a very specific question that is asked by many clients whilst we're discussing scope of services and the benefits of wind tunnel testing, especially for mid-height towers where the client may not be overly convinced of financial benefits of such testing. And the question is, what facade savings can be achieved through wind tunnel testing? So we've specifically selected a modest sized tower, 34-story, 160 meters tall, and we've estimated the material cost of the glass and aluminium with and without the wind tunnel test. So there's some very specific numbers there that we can showcase today. So firstly, Ilham Baru Tower. It's a 58-story, 274 meter high, so close to being classed as a super tall, mixed-use tower. The building structure uses an exposed diagonal exoskeleton or megastrut that provides a distinct aesthetic to the building. You can see that if you can see my arrow going up here, that's the megastrut. We have a cutout or a recessed facade at the ground floor, and again at level 37 at the deck here. We use stainless steel for the exoskeleton and for these diagonal louvres, and they're 4.7 meter long panels span across this exoskeleton here, covering the structure. Now, this is a graphic of the typical system. It comprised of a unitized curtain wall with a low E glass and a ceramic frit at the spandrel locations that also provides privacy. You can see those there, those black bands.
Hi, we seem to be experiencing some technical difficulties on Nikki's end. Let's give him some time for him to sort it out. Nadia, we have a question that was missed for Dr. Goman, right?
Sorry, has my sound come back?
Hi, Nikki. Yeah, we got you back. Yep.
Yes.
Oh,
Just reshare the presentation.
At least it wasn't the blue
Share your
screen of death,
presentation.
but I was very worried there for a minute. Let me re-present. Have I got my presentation back?
Yes.
Hello? Yeah? You can still hear me?
Yes, this is the
Yes.
last slide you were showing.
All right, I don't know how much you missed, so I'll just pick up where I went off and fingers crossed that that doesn't happen again. So I was explaining the system being a fully unitized system with louvres spanning every third panel, as so, and the stainless steel megastrut cladding. I'll move on. And here's the visual mock-up that we constructed. We selected a star node point of the cladding to review how well the stainless steel elements can go together. Various glazing options were considered, and a grey tinted glass with a visible light transmission of 31% and a shading core of 0.26 was selected appropriate, which from the outside looks very dark, as you'll see here, but from the inside looks perfectly clear. That's due to the kind of neutral tint of the glass. So it's yeah, you don't really notice the tint from the inside. So through a combination of high-performance glazing and diagonal shading devices, a 40% reduction of solar heat gain to the tower was achieved. The facade contributed to a LEED Platinum rating award for the project. This is the performance test, a 5-story high mock-up comprised of the typical unitized panel assembly in the upper quadrants, as I'm pointing to here, and then the recessed facade was installed lower than that. So after we'd undertaken the performance test and checked the system was working, we then spent additional time undertaking rainwater runoff studies from the cladding elements, and we experimented with various drainage paths, recesses, reveals. You can see these photographs here where we're inserting to try and achieve the water leaving the panels and taking off any residual pollutants or staining so the panels wouldn't streak. Spent quite a long time playing with those kind of details. So typically for very tall buildings, an ideal facade installation would consist of unitized panels that are launched from nearby floors into position with all the fenestration elements such as louvres, bullnoses, etc., already fixed onto the panels. And all of the launching would happen on the inside face, and you wouldn't go outside hanging off the building to undertake any additional fixing. IB Tower had to buck this trend, however, because of the megastrut cladding elements. So we needed external access via mast climbers to install those megastruts. And you can see here a series of brackets first. After the brackets, we had subframing, and then the panels were installed. So it wasn't the most ideal method of undertaking a tall building facade, but it was necessary for this particular type of installation works. So although the geometrical forms of the panels appear relatively straightforward and are simple triangles, the connection of the panels to structure and the weather sealing of them at these diagonal elements becomes quite complicated. These panels would fix to the beams here, but as you see in certain locations, there's no beams to fix the panels to anymore. So you get panels resting on other panels, and you get very complex geometry at these corners, especially when you try to you try to run the water in a way that it can't ingress and it won't drop into areas where you don't want it. So these 3D images here just show those levels of complexity. In terms of wind and pressure studies, the first exercise undertaken was a cladding wind tunnel test. So we used the Malaysian code 1553 was used to estimate the cladding pressures, and a maximum pressure of 2.2 kPa was calculated. You can see the graphic on the left-hand side here that shows how we undertook that study. During the wind tunnel test, the pressures recorded never exceeded 2 kPa. So this allowed for the facade aluminium member sizes to be reduced accordingly. As a majority of the curtain wall was in a 1.5 kPa zone, which is shown here in blue, we then used that to engineer the profiles, and then we would stiffen them only in areas where we exceeded that. So we never really follow the maximum wind pressure that we get off a wind tunnel test. We go with the majority and then just stiffen areas accordingly. So big savings on aluminium costs as a result of that. For the level 37 external deck, pedestrian wind and rain studies were undertaken along with thermal comfort studies. And these were to check the occupiable spaces. You see we've got seating areas here, tables for eating. There's a water feature at the back here, and it was found that at that height, if those areas were relatively open, then things would blow off the tables. The water feature would be messy and it would cover most of the deck. So we brought in a 2.4 meter barricade around the perimeter there, which shielded against these cross breezes that will give you a problem, but still allowed an ambient temperature and ambient breeze. So you can see there's a very calm water as a result of that study. The architect team, Foster's, wanted to use a bifold door system that MFT had previously engineered for the Dubai Mall project. You can see images of that here. This is in its closed position. So this was a curtain wall with a swing door, but at the push of a button, that would raise and become a balcony, a canopy in effect. You see these graphics here that show that. They were quite excited at the idea of having that would be open for prolonged periods. So in the morning you would raise these panels, and they would stay raised until the evening, and you close it up. So you get this internal external zone that would be more open. The problem being, when we checked the pressures and the study of what would happen to these internal spaces as a result of those doors being open, we got a direct path of air infiltration or pressure infiltration into the lift shafts. So we needed a double lock system, because if you allow these high pressures into your lift shafts, then your lift doors may jam, or the travel could become less smooth and noisy. You can hear the gusts. So there's two concerns with lift shafts in tall buildings that have an influence on facades. So the first, as per the last slide, are concerns with direct air paths through the facade to the lift core. These can come from openable windows, doors, lobby area, louvres, building breaks such as MEP floors, etc. And we've highlighted on this slide here all the various zones that would allow these pressures to go in through the facade into the lift shaft. You get a pressure differentiation as well. Usually the pressure is lower at the bottom and higher at the top. So that creates a flow through the building if it's not managed with airlocks. Ivy Tower was shielded somewhat at the base because of the proximity of surrounding buildings. So that was less of a problem to us. And the second issue is stack effect, or cold condition air dumping through the lift shafts, which could further be encouraged if warm air was coming into the building at higher areas. In colder climates, it's kind of the reverse, with warm air rising up through the lift shafts and trying to draw in air accordingly. But in both scenarios, care needs to be taken to ensure that you don't allow direct paths through the facade, down the lift shaft and out the door, or vice versa. And a lot of tall buildings use vestibules, or in some case revolving doors, to limit this, and then your wind engineer can undertake simulations to evaluate the success of the proposed approaches. So after reviewing of the level 37 wind studies, it was agreed the external deck entrance doors would become automatic sliders. I've got some video footage here. I've got a feeling it's going to be a little bit stunted, but that's one of the architects from Foster's that is walking towards these sliding doors that are tilted forwards, and checking the smooth operation of those particular doors. So with a combination of the sliders automatically closing and the internal doors, we had enough of a double lock there that would work, and we don't have problems as a result with the lift shaft. Now the final wind study undertaken was at the floor area. We did have the recessed curtain walls going into the facade area at the lobbies, but we still suffered from rain infiltration 20 full days a year, and we undertook some analysis of awnings and various depth of awnings to make sure that what we installed within there would prevent rain from being able to enter those 20 days. So that's shown here with the diagram showing the rain infiltration and the final awning installation. So that's the first study, which is of the a guide of the overall types of analysis that can be undertaken on pressures. And for the second study, this is a very specific look at savings that we achieved on one project. So this is Banksar 61, 34-story, 160-meter towers. Client is PHP Properties, and CPP worked directly under Meinhardt. We engaged them to undertake these analyses. So on this first slide, it shows the facade system. It comprises of a fully unitized system with a 450mm bullnose profile attached to the unitized panel. The bullnose is also unitized or separated into two, so we can fix all these external elements onto the panels first, launch them off the building, and we never need to be on the outside of the building. And the next graphic here shows one particular panel, those bullnose surrounds. So we have the panel spans floor to floor, is mounted to one floor. They're very typical in the way that a unitized panel assembly is undertaken. Okay, so wind tunnel testing for the project was undertaken rather late. And at the time that the client team visited the test laboratory along with myself, and we were able to physically stand within the wind chamber and check the pressures at the perimeter of the building using rods and wool tuft. These are cylindrical metal rods with a wool at the end, and you can move those around your building whilst the wind tunnel is operational, and it gives you an indication of where the bigger pressures are. So it's almost giving you like a preliminary result. And from doing this, we could see that the winds along the parapet or the higher areas of the building here were quite strong. We expected that. But also we were getting high pressures at the top of the canopy. So as the wind hits the building, it tends to break and raise and lower. And when the wind is kind of funneling down and it meets the canopy there, you get another buildup of pressure. So maybe less expected than the pressures at the top. There's a little graphic here of wind going around the building and what happens with the pressures as you get a positive, negative buildup at the ends there. You expect more wind around the sides of the corners of the building because you do get drag and pull around those areas. So this was the wind load diagram. That you have the positive pressures and the negative pressures mapped here. And what we did is we kind of reverse engineered the results. So we had a glazing system that was a double glazed 1010 glass. And we looked at if we reduce the glass thickness to 8 millimeters instead of 1010, then what kind of a pressure could that glass withstand? And it transpired it was 1.6 kPa. So we asked CPP to use a 1.6 and map that across their facade using the results of the wind tunnel. And we found that inside the tower proper, where we've got all the unitized panels, they all fell within the 1.6 millimeter zone. On the parapet roof area, it did increase, and down at the podium it increased, but they were using different systems. So we could reduce the cost of the glass within the tower to undertaking that level of analysis on the 1.6 kPa. What we found is that the code was given as minus 2.2 kPa. The wind tunnel test gave us 1.6. So the reduction of the glass from 10 millimeters to 8 millimeters using the raw material glass price of $95 per square meter, but 69. It gave us an overall saving of $450,000 just on the glass raw costs alone. We then analysed the aluminium members, and we could again reduce from the 2.2 kPa to the 1.6. The weight of the aluminium per kg per meter run reduced from 10.4 kg to 6.8 kg. So using a raw material rate of 20 kg per meter squared, we saved $660,000 on aluminium costs. So keeping in mind that this is just we had the bull noses and various other elements that we can make reductions from, but we've just analysed two elements of the facade. And if you add a 10% for a contractor price, because these are raw material costs that we're dealing with, you're looking at somewhere in the region of $1.2 million in savings. And those $1.2 million were on a test that cost $20,000. So for us, it was a bit of a no-brainer. These tests are absolutely worth it. Look at the return on that kind of money, 20K, and you're saving 1.2 million. So I hope that study addresses a question. Every building's different. So every building would need this kind of analysis. It's not possible to be able to say that you're going to get X amount per building. You have to undertake the works. But when you look at the returns, it's a fantastic investment to undertake these level of studies on your facade, even with a 34-story building. And when you take into account that right now materials are up by 30% for both glass and aluminium, then you know it only gets better and better in terms of the saving that you get. So that's the end of my presentation. Thank you. I've got no idea how long I went for. I don't know whether that was 20 minutes or whether it seemed like 5 minutes to me.
You're still in time. You're in time, Nikki, don't worry.
Yeah.
So we have one question for you. Can you see in the panel box under publish?
No, shall I stop? I'm going to stop sharing my screen if that's okay.
Yeah,
and then sure. I can see. All I could see was my presentation. Yeah, my box is not working. You just let me know the question and I'll answer it best I can.
It's from Peter Duffy. He asks, when you conducted the visual and performance tests, was there any technical or quality findings that had to be corrected prior to the final installation?
Yeah, so on the visual mock-up, not so much, because we were really just looking at the aesthetic. We were fortunate with the diamond, the node point connections of those stainless steel elements that came in. It worked very well. The architects wanted 9-meter long panels, and we through a series of conversations with them, we agreed that we would split these long 9-meter panels into 4.5 and then hairline joint them in the center so they would look like 9-meter long when actually they were more manageable as 4.5 meters. But we were concerned that when these came together, because of the intricacies of the patterns, we would get misalignment. And what the visual mock-up showed us was that we can actually control this, and we could, through a series of adjustable brackets, raise and lower and make these adjustments. So we got very clean connections, which was great. When we got to the performance test, the issue that I was talking about just now regarding rain mitigation from the stainless steel megastrut cladding became very difficult, and we decided to open areas. So when rainwater is hitting the panels, it's running. Sorry, the unitized. It's running down the unitized panels, and it's collecting at the base of those, and then it shoots off diagonally into the corner. And we were worried about that collection, so we opened them up and had a series of internal drains or gutters that would let the water run down the back of the panels. So we had to be careful that when we were installing these panels, we didn't have corrosive elements in there that would start to cause rust streaks. We didn't try to seal these panels up. They were gasketed. So the performance test allowed us to do a lot of investigation on what we needed in terms of openings to get that water through there. But the streaking on the outside of the panels was extremely difficult to manage. We tried to open up the joints, and the water tended to jump across the openings. If we added an element in there to flick the water away, it tended to bypass those as well. So what we learned from this is that you have to clean the building on a regular basis, or else you can expect streaking. And no amount of redesign, unless you had some huge areas of recess, which would really affect that beautiful megastrut element, would really help you to stop the water channeling around. So it was very useful to undertake those studies. Other than that, we were good. Yeah, everything went to plan, and the performance test and the visual mock-up were quite successful.
Great. Another question for you. Do we need to do a wind tunnel studies for low-rise building, 6-story?
Well, this is why I selected a 34-story building, as opposed to going for a mega building like going up 300 meters plus. Because if you undertook the analysis there and you get these huge savings, how do they really translate? And if you think that for a $20,000 US dollar test, you're saving 1.2 on 34 stories, then you're obviously going to get some amount of return, although, like I said, it's very hard to say what that return is. So what we tend to do when we get onto a project is we have a first pass at the scheme, and we'll invite either CPP or one of the other wind tunnel teams to have a look at this with us and give some indication best we can to clients. But we always get asked the same question: how much? Yeah, well, what's the saving? What can you guarantee? And you can't really do that. So if you build a series of case studies like the one that I've presented, it will give you an indication of where you can get to with these studies. But there's no hard and fast rule that says that it's necessary. It isn't. We can engineer based on code. And the smaller the building, the more you may not think that it's really going to have much impact on you. But the testing is relatively low cost and the savings are extremely high. So I would think in most cases, it's a very useful thing to undertake.
Another questions. Can you suggest best source or reference for facade commissioning guidelines?
Best source or reference for facade commissioning guidelines?
Yeah.
What in terms of undertaking inspections on site or sign off and handover? I'm not sure I fully understand the question.
Right.
What I can tell you is that the Malaysia has a facade association that are working very closely with CITB, CERIM and other parties to set procedures in place, and there's international codes and standards that we follow generally throughout different regions. So every region would have a set of codes that are implemented by the consultants there that govern these kind of requirements. So yeah, Malaysia's taking strides to formulate their own, bringing in international codes into the local remit, and other regions would do the same. But yeah, it's a case of using, you know, your AAMA standards or your British standards, whatever you've got locally, and fine tuning it to your own environment. I hope that answered the question. I'm not sure I answered it exactly as was hoped.
One more questions from Muhammad Azizan. For IB Tower, can the introductions of sliding door create an airlock area to control the inner pressure? Is it better compared to revolving door?
No, a revolving door would work better because you get the lock continually. Because you've got this cross of four elements turning around, and each one of those goes past a sealed container, you maintain a lock much better. If you have a sliding door, once that sliding door is open, it's open. So you're looking for a vestibule or a second set of doors. And what we did on level 37 is we had the second set of doors near the lift lobby area. So we analyzed how often those second doors would be open and how often we would expect the sliding doors to be opened, and whether that percentage of opening would give a problem to through that analysis, that it worked okay and we didn't have the issue. But if you have doors, you'd have much less of a problem to provide a lock by themselves.
Great. Another question: what recommendation and improvement can be made to our local Malaysian building code, especially for facade element?
Well, this is ongoing. So you'll see over time that, and unfortunately, it tends to be through problems or disasters. So right now, in 2019, August 2019, we had BS 8414, which is a fire code that came in on cladding elements, and it was this was on the back of Grenfell, and we've had 2 fires here as well. And what this looks at is the path of fire going between an external cladding and an internal structure, and that chimney area inside. So there's codes that are coming in now to monitor. And even before that, Malaysia had some codes which are not so common throughout the rest of the world. But floor to floor, inside a unitized system, you have a 900 flame spread separation to stop flames from jumping from one floor to the other floor. In the UK, they don't practice this. There's just a horizontal break. So there's been codes in Malaysia for some time based on fire that are a little bit above and beyond what you would see in other places. Now we're starting to see on the back of the Grenfell fire and various other other fires. We had 2 here, like I said, codes that control chimneys. And unfortunately, when you get a disaster, the codes tend to respond accordingly. So it's whether it's elements dropping off a building, or whether it's fire related or heavy water damage, etc. Codes are responsive to all of these problems. And what you find in Malaysia, going back maybe 20, 25 years, facade consultancy was not common at all. And the more we see curtain wall installations, whether it's unitized sticks, etc., and we get certain damages, flood damage or stones falling off buildings, etc., then the need occurs for these levels of consultancy, and the need occurs for the codes. And those codes are coming in from international. And like I said, there's AAMA, British standards, Australian, etc., the European, the DIN standards. They're being brought here, and there's an association in Malaysia that is looking at these and working with the local authorities in localizing those codes. So it gets better and better over time. But you wouldn't say that there's one hard and fast source that you need to go to and utilize all of those codes exclusively. They do need to be adjusted for climate and environment.
Great answer. Thank you, Nikki.
Absolute pleasure. Thank you.
Okay, before introducing the next speaker, I'd like to apologize for going too fast and miss out questions for Dr. Gorman. Thank you for answering the questions in the panel box, Dr. Gorman. So our last speaker is the country manager for Turner International Thailand, with a combined background in structural engineering and construction management in tall buildings. He has designed and constructed projects around the world. Please welcome Billy Howell.
Hi, thank you, Nadia, and thank you to everyone before me. Actually, hopefully you can see my screen. Okay, so hopefully you guys can see my screen. I'm going to talk about one of our previous projects. It's an oldie but goodie called the Ctbuh Financial Tower, and I'll go through a couple structural case studies similar to what Nikki kind of did with the IB Tower in Malaysia. So I'm going to speak about so a couple of various systems, including outriggers, column shortening, and how we compensated for that, and as well as the helipad. So just a little background on Turner first. I think most people are familiar with Turner and realize that we do quite a few tall buildings, including, of course, Burj Khalifa and KL 118, or Merdeka 118 as it is now, the second tallest building in the world. And some others. I won't go into all the details, but I think people know that. And this is a similar slide showing some of our greatest hits from international. Obviously, KL 118 is missing from this. But this is similar to the slide that Goman had at the beginning of his presentation, a compilation of some of our greatest tall buildings and not so tall buildings as well. I've had the privilege to work on about 5 of these in this picture, and hopefully some more that will appear in the next revision of this one. So onwards to the Ctbuh Financial Tower. So this tower was designed by Carlos Zapata. Well, I'll go into some of the specifics. On the left side, you can see the helipad and outriggers that I'll touch upon. So the tower, 68 stories. It's 262 meters tall, 3 basements, and it has a total built-up area of just under 100,000 square meters. What makes it interesting is that it's a concrete structure with steel elements required, which we'll go into. So the building is iconic. It's obviously, you see its shape, it's different. What's maybe not apparent is that every single floor is different. Every floor is asymmetric to itself. So about both axes, the X and Y axis, there's no symmetry. And every floor is either growing in size or reducing in size. And so that presented quite a few structural structural nuances as well as some constructability issues. Likewise, it's a slender building. It's only it's at its narrow axis. It's only a 1:10 slenderness ratio. Some other facts: it was top-down building, or top-down basements, I should say, semi-top-down. The steel outriggers are at the 29th to 31st floor. The original design was in concrete, which I'll touch upon. The core walls actually vary from 1.5 meters thick down to 400 at the top. And we have columns that actually go from 1.5 meters down to 850. And one of the things I'll focus on is the actual shortening, where the helipad columns have a differential shortening of around 70 millimeters relative to the core wall. So, well, I touched upon these structural issues, or the structural background already, but it's basically a RC building, reinforced concrete building, flat slabs, and so on. But the podium is structural steel, and the lateral system is actually comprised of the core wall and structural steel outriggers, which we did through a revised design. The foundation sits on a 4-meter thick piled mat, and we have piles that go down to about 85 meters. So just a couple structural, well, for the structural engineers in the audience, a couple key facts. The building mass is around 1 million kilonewtons, or 100,000 tons. You can see some of the base shear reactions due to wind and overturning moment, which govern the lateral load design. The dynamic response, that is how much the tower moves and laterally due to lateral excitement, is, you can see it's got a pretty short period for building this tall. It's only, and its longest period, it's only about 5.45 seconds. And that led to an acceleration of around 30 millig's at the top. And this is interesting because actually our office is near the top of this building. And some of our staff can actually feel this movement on windy days. And you know, so much so that at one point the question came back to me. It's like, why does this building move a lot? And the answer is yes. And that was something that was found through the wind tunnel testing. And you know, this actually exceeded the normal criteria for what would be acceptable for lateral acceleration. But the decision was made that it would be okay, and it doesn't affect the overall performance of the building much. So it was accepted, and yeah, sometimes on windy days people can feel it moving. So some of the steel features. So we have the outrigger floors that you can see is highlighted here, and these floors from 29 to 31. Also, there's quite a bit of steel on the building. There's a structural steel podium and also structural steel transfer trusses. So even though it's a concrete building, quite a bit of structural steel that you can see added to it. So these are the outriggers. Apologies for the side view, but that's how they fit best in the picture. But what you can see here is that there's basically 4 rows of outriggers that are, in this case, in structural steel. Then basically the outriggers span from the core to the perimeter columns or perimeter belt walls or belt trusses as we have them. So in plan view, what you can see is that we have basically 4 of these belt walls to connect outriggers here and here. And then where the outriggers had a skew that wasn't too bad relative to from the core wall, divider wall to the columns, we just skewed these. And then opposite on the other side. So it's a combined, outrigger system with belt walls where we needed to catch the columns where the skew would have been too much to handle the relative outrigger forces. We redesigned it from concrete to steel with the contractor for ease of erection. The total steel tonnage was around 400 tons. This was done in Korea, the fabrication, and then erected in a total of about 10 days, which is very good for outrigger construction. Granted, this isn't a full outrigger and total perimeter belt wall or belt truss system like you see in some buildings, but overall, it was something that was done pretty quickly without slowing down the floor cycle too much. So, and another key feature which we'll discuss is that they stayed disengaged until the tower was topped out. So basically, we didn't want the outriggers carrying the floor loads from the perimeter columns down to the core, and I'll explain that a little more after. So this, for the structural engineers will recognize this diagram. What we're looking at here is the overturning moment of the tower, which you see here in blue. And then basically, the overturning moment is resisted by the core wall and the perimeter columns acting as frames. And then so what this line is the, what the core, if there was no outriggers, the core would basically resist this much overturning moment. However, once we add outriggers to the system, the outriggers basically resist, similar to say a skier or somebody that extends their arms out to their ski poles. The outriggers actually reach out and grab the columns and then take that overturning moment from the core at that level and help distribute it to the perimeter columns over a wider section. That helps resist the overturning moment in the building. And in this case, that resets the moment at the overturning moment of the building at this point, and then adds to this reduction in overturning moment over the height of the building. That is the reduction in the core's ability to resist the overturning moment. So when we first started the project, actually the intent was to have the outriggers be in concrete. And we had a very good concrete subcontractor on site, and they were doing a pretty good job with the flat slabs and the core walls and so on. But as we got into it with them, we realized that the design for concrete outriggers was going to be extremely difficult. Basically, this is in a time where we weren't really doing a lot of 3D modeling for rebar. This is sort of the earlier days of BIM, and basically we would have required 3D bar bends with D50 rebar, that's 50 millimeter diameter rebar, as well as post-tensioning through the top chord of the outrigger. And so it was a very complicated rebar system. It could be done, but it was extremely complicated, and we were concerned that that would have been a bit difficult for the contractor to complete, and we decided to go back to a steel. We decided to go with the steel option. And also there was the issue of this diagonal, as mentioned. The diagonal portion here was meant to be disengaged so that the column loads, where you see these arrows here coming down, would stay in the column rather than being diverted through this rather stiff outrigger element as the building is built out. So we didn't want to do is have to basically come back and concrete this outrigger element where it was disengaged after the building was topped out. I mean, it could be done, but it was going to affect some of our sequencing in terms of schedule as well. So we then moved on to a steel option, and what you can see here is basically we have steel plates up to 60 mil thick that run through the core wall. They hit nodes at the top and the bottom and top at the interface of the core wall. And then we have elements that, these node elements that transfer to beams or diagonal elements. And so in essence what this is a composite outrigger system. So in order to carry the shear forces that are associated with the outrigger cords going through the core wall, we needed these 60 millimeter plates connected through, as you see here, along with, this was an option from the contractor. These are pins, actually, physical pins, to allow the rotation of the disengaged cord. And so this is an enlarged version of that. So when we started this seemed like a good idea. We said, okay, we'll have the pins. This will allow for what you see here, whereas you can basically move these guys and swing this lower element up into place. This guy can be swung up, and then we will close this diagonal gap once we top out the building. And this diagonal gap was actually very easy to close once we basically just filled it with thick steel plates and then welded external plates to these box sections. However, one of the challenges we realized after we got the pins in is that if you can actually get a pin, here I'm gonna go back. If you can get this pin to go through these 4 plates plus the other 5 plates from the adjoining member, if it can go through easily, you have too much slack in the pin system. And then that means that before you can actually engage the outriggers, there's going to be too much stress on the core wall. So then we actually had to go back and refit these pin elements to give them a tighter fit. And that so although we had the main outrigger system in place, we actually had to, while we were continuing to construct upwards, we had to go back and refabricate these and refit them to get them in. So there was a lesson learned there. These are some images, again, of the same. And then this is the system overall. So here you can see this is one of the diagonal elements. It's pinned, and then, like I mentioned, it will be swung into place later. And you know, likewise there, and so on. So overall, this was very successful for us. As mentioned earlier, basically these were erected within 10 days. We realized we wanted to make this change in the from concrete to steel around the 10th floor of the building when we were at the 10th floor in terms of construction. And working with the contractor's engineer, myself and a guy from Hyundai named Ko Hee-jung, we were able to go back to the designers, the original designers, and work out this this system. Basically, they let us make the substitutions. You know, matching the steel in terms of strength was pretty easy. One stipulation they had, of course, was that we had to match the stiffness. So some of these elements became concrete-filled sections, even though strength-wise they didn't need it, but stiffness-wise they did. And yeah, overall very successful, and led to an early completion of the structure. We ended up finishing the building structure about 2 months ahead of schedule. So moving on from the outriggers, next consideration, and this was a big consideration for us, was the axial shortening. And axial shortening is something that's common for all of us with super tall buildings. And even though this building's not quite 300 meters, it's not really super tall, but it's something that we deal with frequently, you know, in the 250 meters and up range, where you end up having higher stress levels in the columns, typically the perimeter columns, and less stress levels for gravity loads in the core. And because of that, due to initial loading, the perimeter columns will potentially experience more elastic deformation or initial deformation. And then if they're concrete, they're subject to creep and shrinkage. And then so with that, you actually get even further deformation over time, especially in the first couple of years. And so the engineers for the project, Lyra, in their original documents, they said, look, you know, we have predicted these shortenings with an initial analysis. And so what you can see is that they had some columns, these guys, that were actually expected to settle or to shorten by around 150 millimeters, and then the core wall, the closest portion core wall, only around 80 millimeters. And then with that, that meant that we had about 75 millimeters difference in, you know, height at the 50th floor between here and here. So to compensate for that, well, there was 2 steps. One is we needed the contractor to do a more in-depth analysis, because this was preliminary. And then also we need to determine the actual concrete properties, and then do some more rigorous analysis, and then determine a compensation methodology to make sure that overall that the building wouldn't have sloping floors or some issues with that. So the first step in that was determining the actual concrete properties. We did creep tests, long-term creep tests, and shrinkage tests. And I think most people know that, you know, creep is deformation due to sustained loading in concrete. And so all concrete, you know, where you see sometimes balconies on old buildings that are starting to deflect, or sometimes stairways that are sagging and things like that. That's, you know, that's evidence of creep through spanning. And likewise with columns, the same thing happens, is that they just get shorter, or they under sustained loading. And then also concrete subject to shrinkage. And so what you see on the left side, or on the right side here, is these guys fitted with strain gauges and looking for their shrinkage over time. And then of course this left side, where these guys are under sustained loading, and to determine the actual concrete properties. This data from how the concrete would actually act and respond to sustained loading and shrinkage over time were then plugged into models, basically, that followed the building sequence, and then that was used to determine how much we compensate the building, or how much we compensate each column or not. to determine, in order to keep the building flush, not leaning, and then keep the floors flat. So what you see here on the left side is a plan where we had all of the various instrumentation. And then, so in each column and at various core wall points, we had a lot of these sensors. They're connected to multiplexers and data loggers, and then wireless modems that then, get basically monitored throughout the project. So we could look at these in our office and basically know how much strain or deformation these sensors are undergoing. So this was actually field installation. This would be in a core wall where we were installing some of the sensors. Of course, the same. And then this is, of course, being embedded within a core wall. So this is one of those 1.5 meter thick core walls with the strain gauge in the middle. And then this is connecting the multiplexers and data loggers. And what's that lead to? So basically, as you build the building, every time you add a floor to one floor going up, the building sinks a little bit, or the columns have to absorb that additional load. And then so you can predict, and what you can see here is like you can predict that, okay, as we build the building going up with time, that there's going to be a certain strain, certain deformation of the columns where they're expected to shrink basically, or to settle by this much. And so you have the predicted line, and then you have the actual data readings that we had. And so, what was actually predicted and measured lined up pretty well, except for this guy. This guy was obviously a bad sensor, so we had to do some additional surveying, basically physical surveying and double check. And eventually we realized that, well, that was just a bad sensor. So, the other 15 out of 16 were operating properly and as predicted. And then this leads to basically a compensation strategy where we figured out how many millimeters, as it was per floor, that we needed to add to basically a vertical camber, if you will. So basically how much you have to extend the column length with each casting in order to make sure that when you got to the appropriate floors, that over time, at topping out, and then over time, the floors would settle to being horizontal. And so what you can see here is basically we got up to 60 millimeters and 40 millimeters on some of the columns, but they had to be basically over cast, so that you'd actually have a floor that's tilted up when you're casting it, which is kind of shown by these guys in an exaggerated fashion. But basically you have some columns that have to be overcompensated, cast higher than normal, and then the slabs, of course, being tilted up to match that, with the intent that they will, with the final loading, they will settle back to a horizontal, to where the floors will be horizontal. And then what's that lead to on site? Something kind of simple in the end is basically adding, extending the column forms as needed. And so basically you can see that we had to shim 5 millimeters at a time on the column forms. And but it's a key about tracking this and knowing what this is, and then monitoring it through iterative cycles through the data loggers. And eventually it came out okay. There's no sloping floors in the building, even though some of the columns ended up being 60 meters out of place, or it's basically cast 60 meters higher than it should be. Everything ended up flat. Next is the helipad. So here you can see the helipad from above. So this helipad is at the 50th floor of the building. It's a steel structure also. So again, the base building is concrete. And the helipad is cantilevered, and it's basically got two columns that are located here and here. And then this dimension is about 25 meters out. So it's about a 25 meter cantilever, and it actually cantilevers over the street. So these last 6 meters are over an active street below. So this street that you can see here, this street is an active roadway, and this is over that. And so when we were erecting these last couple pieces, we actually had to close the street, but overall that street remained open up until that edge. And so that led to, a somewhat unique strategy in how we had to build this. Overall, the dimensions are around 40 meters going back from here to here. And it's not been used for helicopter so much, unfortunately. It is a great public event space, but it's not been used for that, but it is designed for it. So maybe one day that'll become more of a common thing. So some brief facts on the helipad. It's 260 tons of steel in total. This is the 40-meter length, and then the 22-meter cantilever, as mentioned, off of these two columns. The largest shape depth is 2.6 meters. It's basically just built up eye shapes that are tapered with flanges that are up to 125 millimeters thick. And the heaviest member on this was 23 tons without the connection plates. And when you add the connection plates, it adds another 2 tons to that. So this is crane on the project. This helipad is what determined the size of that crane, because basically we had to get all the way up to the 50th floor before we could even start erecting this. This was again fabricated in Korea and Vietnam, and this was pre-assembled at the factory here in Vietnam prior to being erected, and that was its own unique event. And so I'll show some pictures from that. And yeah, this was done with around 4,000 bolts. So this is a bit of the geometry from the architect. And then this is a 3D rendering. You know, again, this is kind of before BIM was common, so these were just early, 3D models. We did a lot of both physical and digital models at the time, just to make sure we got the geometry right. This is them in section. So again, this is like 2.6 meters deep at that point. And then this is the actual member, and that's the 2.6 meter deep section. And that's me on an inspection in Korea during the winter, at very cold, hence the dress as such. And then we got all the pieces to Vietnam, and what you see here is actually a pre-assembly. And so this is one of the things where early in the project, when we looked at this, we said this is something we added to the structural specification. We said this needs to be pre-assembled and completely built, and then disassembled and built on site. And the reason for that was we wanted to make sure everything was fit up. And even though it was in the specification, as things happened, the fabrication was a bit delayed, and there was a rush to get things up, in time to complete the project or complete the structure. And we ended up having to argue a bit with the contractor, because there was a push from some of their people saying, look, we don't need to do this. It's been fabricated properly. We'll just put it up on the building. And we had to fight for it, but eventually we won, and we said, look, we're going to fabricate this on the ground, or we're going to erect this on the ground, make sure it all fits up. And when we did that, we spent 3 weeks reaming bolt holes in order to make it all fit. So you can imagine we had 4,000 bolts on this, and there was quite a bit of reaming and rejigging and adjusting some of the connection plates that are much easier done near ground level, where you can just build the scaffolding up and work on them, as opposed to having to do them at 50 floors up and over an active street. So this is one of the things that worked out quite well in terms of pre-assembly, and highly recommended anytime there needs to be something like this, some sort of feature like this pre-assembly before will save a lot of trouble on site. And in the end, this is it being erected. There's one of the larger, not the largest, but one of the larger pieces being lifted up with the connection plates, sort of in an alligator mouth to be fit up. You can see the Vietnamese flag and the Communist Party flag there flying. This is the initial girders being up, and the cross members cantilevering off of those. So it's 2 primary cantilevers with subsequent cantilevers. There it is in its full structural state. This is taken from the crane above. This is, again, in the days before drones. And then this is the metal deck. So metal deck and studs. And then this is the after the concrete was cast, and not really the best job of curing, but it is what it is. And then this is us replicating a somewhat famous picture from that you see from one of the high rises in New York, where you have the construction workers sitting across the beam, I think from Rockefeller Center. So this is us on one of the cross girders, and I'm in the center there, along with some of our team members in Vietnam. So in the end, you have to sort of make a moment of it and enjoy the time after you complete it. So that's the end of my presentation.
Thank you, Billy. We have 2 questions.
Okay.
Can you check in the chat box?
I need to stop sharing. Hang on.
It's in the chat box. Paige Mandy
Under
asked.
chat. Okay, sorry.
Yeah.
Okay. So how long does it typically take for the settling to result in the horizontal? Okay, so the so if you look at the there's 2 types of settlement when it comes to axial shortening. You have up to and sub to. So up to is sort of the elastic shortening that happens with initial loading. Then sub to is subsequent to, meaning that after you're in place, you have additional loading coming, the elements start to settle more. And so the elastic happens almost immediately, but it's incremental because every floor you build up adds a little bit more weight to it, and it shrinks a little more. You add a little more, and it shrinks a little more. You add a little more, and it shrinks a little more. And then after that, you have creep and shrinkage under sustained loading. Those typically happen mostly in the first year. So, which is one of the reasons that basically we sort of we keep the outrigger disengaged, because again, with all of that loading, once you get topped out, which probably takes a year on a project like this, then you know, a lot of that deformation has already taken place. You don't have to worry about subsequent creep and shrinkage at the lower columns, then basically causing it to hang or something off the outriggers. So we expect to see most of this within the first year, and it depends how tall your building is. If you have a 600-meter tower, the structure actually, you know, that first year of deformation is going to happen while you're long before you actually top out the tower. So you know, it's different at each level, but basically within the first year, and especially within the first year of topping out, if you look at the curves, you'll see most of that. And then certainly within 5 years, it would mostly be settled. I mean, in the end, concrete will creep forever, but you know, the majority of the effects due to shrinkage and then also creep will happen within the first year or so.
There's another question.
Yeah. What is most critical when installing these heavy steel structures? So that one is interesting. A couple things. One was actually just getting the members in place. So one, you have to have a crane big enough to lift, and then 2, you have to be able to control that member as you go up the building. And so as you deal with tall towers, what happens is that you have winds that change at different levels. And so we had flags, for example, at every 5th floor, as well as anemometers to see, you know, what the wind direction and the wind speeds. And then what we saw was that actually that we had winds at, you know, lower portion of the building that were, you know, in one direction, and at the upper portion of the building in another direction. And so you're lifting this 20-something ton member that has a big, wide, flat area, and you have to bring the crane up, or you have to bring it up with the crane, and you're resisting winds one way, and then you get to a certain height, and then the winds shift, and they're swinging it the other way. And you have to make sure you don't hit the building, and it's actually not the easiest thing. You can't tether this. You know, if you're doing lower steel picks, you can have a rope onto it, you know, and then people can kind of guide it with the rope for the, you know, couple of floors. You can't do that for 50 floors with a single rope to kind of control it. And so I would say that the control, in the end, we found a solution. It's actually not, it was a good solution at the time. I won't repeat it here because it has some implications, but basically we figured out a way to bring up these large members and control them with, using combined facilities, let's say. So I would say that's it. It's basically getting it into place and making sure you can control it on the way up, in particular for shifting winds.
Thank you, Billy, for a good presentation. So for the next program, we will start with our panel discussion, where we will discover the challenges in tall buildings. Our panelists will cover topics ranging from planning, design to finishing the job, and how we can incorporate green energy into constructing tall buildings. Here we have our moderator, Sean Mills, who will lead the discussion on today's topic with our panelists. Over to you, Sean.
Thanks, Nadia, and just want to say what a great bunch of topics today. I really enjoyed it. Thanks to all the speakers for all the hard work they put in. I'm sure the audience has really enjoyed it. But now to the most fun part of today, for me anyway, is the panel, and I'm looking forward to see what you guys have to say. We put together a few hot topic questions based on your presentation and on what's happening today.
Sean, we can see you. Sean, you need to on your video. We can't see you. Sorry.
Are you sure? I can see myself, Nadia.
Can't see you, Sean.
No, okay, let's try it again. That working? Okay.
Yep.
Great, thanks guys. Must have been a glitch on my side, apologies. So anyway, let's get going. I think what I'd like to do is direct the first question to Peter. So Peter, this is a really hot topic today, but given the global focus on carbon and climate change, how do we feel about tall buildings as a typology? Are they still relevant? Are they appropriate for the future city?
Great question and difficult question to answer, but of course, I believe, and I think most of the panelists here believe that tall buildings are relevant and are actually more important than ever. As part of my presentation, I was saying that, you know, it's not the height, but, you know, the quality that matters. And because more and more people are moving to cities and urban conditions will only become more intense, height is part of the solution, and technology can continue to improve and make taller buildings and these mega tall towers and beyond habitable. Now there's new technology to you know, make these buildings not only less carbon intensive, but actually sequester carbon and produce oxygen, grow plants, generate energy. So there's new technology that continues to get developed, and I only think that we will have a better chance making these greener and more sustainable.
Thanks, Peter. Great answer. I'm going to do a follow-up for you, Billy, I think, on that point. So he spoke of new technology. What do you think are the ways we need to change the way we envision or construct tall buildings? And do you think the debate, I mean, it's easy to point the finger at high-rise as a, you know, a carbon-hungry beast, but is that really the right way to frame the question?
Well, so Sean, I think that, yes, you know, it's all about materials and sustainable materials, right? And how we can be more sustainable and what we do to, yeah, you're right. The building industry, you know, especially the production of cement, it produces a lot of carbon, right? But there's new technologies out there to capture carbon within concrete. I mean, the downside of that is at some point the building comes down, you re-release that carbon, but you know, compared to other things, you have to catch the carbon somewhere and put it somewhere. And so keeping it sort of in a long-term storage inside of our structures is one element, right? And use of timber, what we're seeing more and more of, right? Timber, you know, not really high rises per se, or depending on where you are, how you define it, but use of timber, which is of course, you know, a lot more sustainable. I think it all comes down to just being, you know, sort of responsible custodians when it comes to design and thinking about how can we be more sustainable on our materials. You know, and it's a holistic view. Right? You can't just sort of say, well, we're going to use this recycled stuff, or we're going to embody carbon here, or offset it this way. I mean, it sort of has to. You have to look at, you know, from the design standpoint. And I'll let the designers give probably a better explanation than I can. But it's like, you know, we see this a lot, like, you know, floor-to-floor windows, and you know, so you're bringing in all this heat, but then we put sunshades. It's like, well, you know, but you see other cities, they say, no, you have to restrict your window-wall ratio so that it's, you know, so you're not emitting, you know, all of that and losing energy one way or the other. So, you know, there's, you know, yeah, I think just everybody just has to kind of keep it in their mind and then look for sustainability through materials and then just through holistic design.
Can I go back to that first question?
Sure, Nick.
And just add a little bit to what Peter said. So recently we had the UN Climate Change Conference, or the COP26. There was 44 architectural firms and construction businesses that signed up to this World's Green Building Council on net zero carbon building commitment to have zero emissions by 2030. 44 is not a good number in Chinese. Yeah, it's say die. They should have got 48. Then it would have been die prosperous. But at the same summit, at the same conference, there was concept design shown that presented skyscrapers that would remove carbon from the atmosphere using hempcrete, certain timbers, and various other materials. And it was stated that these examples, these concept buildings, would sequester over a 60-year lifespan of the building. They would sequester 400% of the carbon that was used to construct them. So that's quite an interesting approach to show that maybe tall buildings will help, like Peter was saying, they'll actually help with carbon emissions as opposed to add to them. Another interesting approach is to sequestering carbon with algae. And now algae is quickly becoming a buzzword in the field of bioarchitecture and energy production. The likes of BP and Exxon, they're putting money behind biofuel projects. And algae facades are becoming increasingly seen as a solution to problems of sustainability and ways to power buildings. Aside from being able to produce biomass and hydrogen, they can also use to detect pollution and absorb carbon dioxide whilst releasing oxygen at the same time. It might not be suitable for every environment. Like over here or in the Middle East, you just end up with boiled algae. But in a lot of places, maybe this is a fascinating approach. And they've just finished the construction of the world's first building in Germany that uses an algae bioreactor facade called BIC, or Biointelligent Quarters. And that's a zero carbon apartment complex that was constructed as part of an exhibition there. It's quite interesting. You've got these bright green or lime green panels that's kind of the algae basks in the sunlight and it's fed nutrients and then it's harvested as well, which is quite cool. And there's a proposal, there's a proposal also to reskin Chicago's Marina Towers with algae on the top of the tower and then around the car park ramps in tubes. So it looks like it's gaining traction that these kind of technologies are going to be explored and implemented further. So it's quite exciting.
Yeah, very exciting. And boiled algae sounds very tasty, doesn't it? So,
yeah. I also want to contribute a bit here.
Sure, jump in, Dr. Broom.
For Arab was one of the companies who also involved in the COP26, right? COP26, and also signed at least we're going to have all our new building will be we need to calculate the life cycle carbon, right? The LCA. I would see that, for again, tall buildings, it allows us to have more room to use sustainable material, because the amount of material you order are far more than like building a suburban or a low-rise building, because the amount of volume, and we can have a good bargain on the cost as well, right? And now we've been using new material. There's some new cement replacement, right, which could be up to reduce the carbon by 75% of carbon in concrete, right? That means that it's only like a normal concrete divided by 4. So it makes the concrete more sustainable, but of course we still need time to be for that material to be commonly available in the market. But if we have a tall building with the volume request, right, so it drives the market. So I would see that this is probably tall building is still a bit of the future. Now again, if you look at there's one book published by Council of Tall Building, right, Urban Habitat by Anthony and Peng, probably 5 years ago, they make a study on the tall building versus suburban. And then the conclusion, I mean, well, there's many conclusions. One of the statement is they found it the total energy for a tall buildings or tall building city is more energy efficient, right, than a suburban. And also, you look at the report by the Association of Energy Conservation, and they made a study on London. And then they found that the energy consumption of London, London is, well, they do have a bit of tall building, but not a lot, right, at the moment. And you'll find that the transportation energy consumption is half of all the domestic. So it's a really large amount, right? Or like, you know, nearly 60 million population in Greater London. And then they spend the energy in the house, yes, for like the whatever electricity and so forth and heating in the winter. And then they spend half of the total energy in their transportation. It's because the diameter of Greater London is too large. And then people you're traveling in a horizontal manner and make the whole city, you know, not that energy efficient.
That's a great point, Dr. Gorman, and I actually kind of tried to tease that answer out of one of you guys. I think that's a fantastic study you're referencing. We'll put that on the, you know, the chat. Hopefully, the people can see, but it definitely shows, at least up to a certain height. I think the cutoff's around 50 or 60 stories. That definitely tall buildings can be a lower carbon solution. So just following up, I think one for you, Dr. Gorman, and maybe Billy as well. Now, you've both had some really amazing careers and designed many, you know, landmark tall and super tall buildings. And, you know, we've been talking about new technology that's come up a few times today already. And I just want to zero in on the kind of structural question. You know, I'm a structural engineer by trade as well, and a big fan of a lot of topics you've been mentioning. But, you know, what do you think of the, you know, the latest developments where we're starting to try not to view our structures as static objects? Designing them to be adaptive over their life cycle, not just around the changing space as Peter would like, but also maybe that they start to adapt in terms of stiffness and response depending on what types of loads they're subjected to. You know, buildings like you've seen the Fremont Tower in San Francisco, which has an adaptive damping system. But also kind of a follow-up question to that is, you know, Billy, you mentioned the concrete needs to be pulled down and that carbon needs to be released, but what about some of the new approaches around demountable structure? And I guess let's start with Dr. Gorman and maybe a follow-up with Billy on that. That's kind of two-part question.
Well, I mean, for us, I mean, for Arab, I mean, we also been studying for quite a long time, and we try to make, now we have the word of design for demountable, design for deconstruction, right? And because I think for now, for in terms of carbon, I mean, the majority are the upfront carbon, right? Where during construction, and then there's operation, and then there's recycling. And I would say that, you know, this is probably like one of the change in terms of the structural system. But at the same time, you're talking about adaptive structural system. We do have some this kind of structure system in around the world in various kind of manner, and also say we have probably, I don't know whether you know, we have a what we have an IP patented shear fuse outrigger, which is a composite outrigger, which the outrigger behave as rigid. And then it will start to yield in severe earthquake, something like that, and then we can just replace it, and just like replaced by a fuse, right? And also we do have a couple, but it's still probably in like a research stage of having a smart structure system and to change the stiffness of like a damper, and which provide a stiffness in certain direction. But the moment is still under research because the response time of computer and the system, you need to be very quick and so forth. So, but I would agree that some sort of later, when we have a more commercial available of the smart metal and so forth and so on, I think the age will probably change, right? And this. And also, if you look at my one of my book in Outriggers, right, also published by Council of Tall Building, and we have an idea probably 30 years ago of having an outrigger which, with an oil jack and then shift the stiffness from one end to the other, etc., etc. I think this is kind of, idea available. But of course, I mean, in certain days, when the technology is really available, then we can use it, As mentioned in my one of my slides, yes, we need to fulfill the function, the statistics, sustainability, and one of the issues is whether the technology is available, right? I mean, in terms of material, I mean, we need to have to keep the idea, but maybe someday, maybe tomorrow or the day after, the material technology really can exist, right? Then we can use it.
That's really hopeful, and I think that this will be one of the one of the gadgets in our toolkit that'll help us decarbonize tall buildings. But Billy, how about a follow-up? I mean, as one of the biggest management companies that actually build stuff, do you see this as a practical solution, or some of these trends are realistic, or just the fancy of of us designers like Peter and so forth?
So I think there's the possibility, but as Goldman mentioned, with the technology being developed, I mean, and it depends what you're resisting, right? Like, are you going to have a system with a variable stiffness in response to earthquake loads or wind loads, right? Wind would probably be a lot easier to handle, because the earthquake magnitude, it could just be a little tremor, and then what I mean. There could be there's a lot to go through and to understand that that all of a sudden that you wouldn't want to overcompensate or undercompensate in one way in response to what's happening, and it needs to be instant, right? And that timing is difficult. So I think with time there will be something like that, but it sort of sounds like you kind of these systems sound similar to like the autopilot type systems, in aircraft and the compensation systems, where they're sort of responding to external input, and then governing what the internal input could be from pilots. In this case, it would be automated. So that I think there's a lot to be developed there. In the end, and then there's a cost associated with that, and that would it actually make us more efficient in the end? I don't know, but it's certainly it's exciting, and there's that side of it. You mentioned also demountable, and this one I don't want to be cynic, but I'm a little doubtful of the demountable thing, and if I think of things in a smaller scale, I've been on several projects where I've had clients say, look, we're gonna repurpose our sales center. We're going to, have the sales center here, then we're going to move it over there. Or we want to make sure that we can disassemble everything and rebuild it somewhere else. And every time they've designed it this way, and then it all just gets chopped up and recycled. So, I'm a little, little more cynical about, demountable and actually, and in the end, if we can, okay. And in one sense, you see it with structural steel anyway, right? But even then, when you see structural steel buildings being demolished, right? You see people burning through them, burning through the members rather than unbolting. And so, yeah, I'm a little more cynical on that. There's something there, but again, it has to be looked at holistically. And
that's great, Billy. And I was hoping you'd be cynical because I wanted to ask Peter about this next, actually. So, we've seen, at least I'm seeing clients. Particularly post-COVID, that with the way workplace is changing, there's a demand on flexibility of space. And so maybe full demountable super tall isn't practical, as Billy is mentioning, but what about, smaller scale movable floor plates, and so you can expand and change things up the building? I mean, I've seen examples of that, like I think it's called the Kai Tower in Sydney. But how about at Gensler? Are you experimenting with any of this? Do you see a demand for future flexibility and demountability? Peter, I think you're muted, buddy.
Apologies for that. Certainly, there's a high increase in demountable walls, floors, and design today. Just recently, we did a design review for one of the tech companies, and they wanted all their partition walls movable and demountable. And you know, flexibility, adaptability, and not knowing what the future holds is kind of the key word here. So if it's, I agree, at a smaller scale, this is more practical. It's more like furniture or, you know, fabricated architectural components, which makes it more realistic. But when we're talking about structural systems and, you know, behind the scenes equipment, I think that's when it becomes tougher. Also, you know, when there's a time gap, the people who install and design, and let's say 5 years, 10 years later, you think about changing the space. You know, what the original vision and ideas are kind of lost. So you know, that's more on the software side or the management side of how to utilize these. But definitely there's a big push in adaptability, repurposing spaces, and demountable architectural elements.
Thanks, Peter. I think I'll do a follow-up with you, Nikki, on this. I think glad you brought up repurposing. So, you know, I think we only build about 2% new a year of all of the square meters that exist on Earth. And so, and particularly, you know, not to pick on facade engineers or cladding, but there's a lot of buildings out there that have, you know, they're distressed assets because the cladding solutions, which were produced and mounted 20 years ago, or you know, the gaskets are failing and they're no longer really practical for the kind of solar gain we're trying to manage. So, Nikki, are you seeing a move, you know, for recladding of buildings, or how to deal with this, you know, which could be a real problem in the coming, you know, 5 to 10 years. There'll be a lot of pension funds with distressed assets. They won't be able to lease them. They won't be able to, they'll have to knock them down. And that's a whole problem from a carbon standpoint anyway.
Yeah, I'll give you one example of a building that tried to address climate concerns and now has problems. An Al Basar Tower in Abu Dhabi, which has these, and it's a really attractive facade. It's got these beautiful panels that open like petals to shield the facade from direct sunlight. So they respond to the path of the sun, but they're controlled by motors that are now, I think the building's about 8-10 years old. The motors are now breaking down and there's no replacement parts for them anymore. So they're really having a problem now to resolve what to do with all of these electronic components that they can't replace. So, you know, yeah, as in facades more than most other technologies within a construction of a building, the technology changes very fast. Even in glazing, well, glazing that you're putting now, several years from now, it's very hard to get replacement panels that have the same spec because it's moving all the time. Recently, I spoke about the Glenfeld issue and the fire concerns earlier. It was one of the questions at the back of my presentation. In the past, composite panel cladding was seen as a very economical way to clad a building and to give it a nice aesthetic while shielding, maybe disguising some of the structure and whatnot. But now you're getting these integrated systems where you need to have testing on not only the panel but the frame behind it, and then insulation blocks with intumescent coatings separating all of these areas. It's no longer the economical solution that it used to be. So as these kind of changes come into play, we're going to see facades start to adapt accordingly. It may not affect the tall buildings so much that are using all these curtain walls that have the, you know, the unitized assembly, because you don't have the same kind of gaps. they're mounted to the slabs, and those panels are the break between the inside and outside. But cladding in general, and whether that's stone cladding, GFRC cladding, solid panel, composite panels, they're going to be questionable in terms of economy because of the way that the requirements are going in terms of fire. So we're going to see some adjustments. I've got colleagues in Australia that are saying that they're seeing more brick returning to facades now as a result of this. And, you know, the industry is changing. There's the local fire regulation or the local fire authorities here called BOMBA issued a flyer earlier this year that said that, well, firstly, it was pushing for these BS 8414 regulations further, but it also made a statement that said that any building that was clad with a combustible panel in the past has 3 years to take that panel off the building. We don't know at this stage whether that's going to be put forward and really enforced, because the ramifications to that, if you go back 15 years here, 20 to 15 years, you didn't really have these Class O rated panels. They were all combustible panels. So any building that was before that time, they're covered in this. And the implications of for a building owner now to strip their building completely, especially in this economical climate, will be devastating to them. But we've seen
really
that.
Interesting.
Sorry?
I think that's really interesting. Personally, I'm a big fan of, government intervention on some of these really critical issues. But you're right. I think you're going to create, if this is enforced, which I hope it is, it's going to create some real issues for a lot of our asset classes, and potentially a real moneymaker for facade specialists like yourself, right? But Dr. Gorman, you had your hand up, so you wanted to.
Yeah, I think I would like to respond about the demandable structure, that kind of thing. And in 2018, Arab has done a 28-story high building in New York, which is by means of modular construction, right? By steel module, by bolts and nuts and so forth. And so basically it can also be demandable. And then put the module, the unit could be removed and then replaced, or moved to other places and rebuild the building, or maybe part of the building, whatever, right? So I think modular construction besides is demandable because it also off-site fabrication, and in terms of carbon will be much lower than in situ. And I think this is modular construction probably maybe one of the way to go, especially for domestic use, right? For offices and other maybe a bit difficult because of the building services, etc. But in terms of like unit-wise, like a living room, bedroom, washroom, or toilet, everything, I think would be quite adaptable, right? And for this kind, and I think demandable is probably one of the way. And you also probably some of you may look at some YouTube showing, you know, building in China will build 30-story or 40-story in 20 days, and all these will be prefab and also by bolt and nuts. That means that, but alternatively, besides the speed, but because it is by bolt and nut, it also means that it's all demandable, right? And replace, right? Would be moved to somewhere else or recycle and so forth. Shouldn't be a big problem for that. I think this is probably, we are not in that era yet, but again, sooner or later, it will probably be the case. Yeah.
Yeah, well, I hope it's coming, and I think you made a good point that, you know, all of this is possible. But as Billy says, even when we have the best will in the world, there are other demands economically or functionally that drive us down. Just knock it down and rebuild it. So I guess that comes back to, you know, there's a lot of different regulatory bodies out there. You know, there's, you know, lots of certification systems, green building indexes. What do we think, if we're really going to make this kind of change and move forward some of these big agenda topics, what do you think is the role of government in making this happen? Best example I can give you is where I'm sitting in Singapore, where PVC is, one of the dominant construction typologies for residential, but that took huge investment in, basically creating a regulatory environment where you can't play unless you go modular. So is that the right approach? Who would like to tackle that one? I'll leave it open to the floor.
I'll have a quick one, because we had GBI, maybe going back 12 years, GBI, Green Building Index in Malaysia, was brought in with tax incentives, and developers were told that if the cost of going from a standard construction to a green construction, you will get that back with a tax incentive over time. And that was a great segue for bringing in a change. And then over a period of time, when it was accepted as being more the norm, the incentives were taken away, but the legislation came in. So if zero carbon could be something similar in approach, but then you need a government to be able to provide those incentives. In Middle East, for example, the tax isn't there like it is over here. But the conflict or the issue is, if you start to enforce something within one region, and it gets very expensive to develop in that region, and then you have other regions that are not doing this, maybe developers move towards other regions where they can get a better profit. So there's that balance to be had on how do you push something forward whilst, maybe it's a carrot and stick approach where you give an incentive, but you start to push legislation. But it has to be something that is looked at globally. What do you do with the guys that won't play? Embargoes, maybe? Some kind of either a tax to an end user on a high carbon facility, or embargoes on countries that won't come to the table. They're very difficult things to resolve, but yeah.
That's a good question. I think, what you brought up around, the movement of capital and the regional approach, maybe as a follow-up, who wants to pick up the next segment, is how do we zero in on that in a Southeast Asia context? This is probably the biggest, most aggressive growth areas in the world, but I think there's a lot, at least the perception is that there's a lot of things that we could adopt that are happening elsewhere that could benefit not only the carbon position, but also the outcome of the quality of the development. So Billy, give you that softball one.
Oh, geez. Yeah, that's not a softball. No. Well, okay, just a couple of things to go back on modular.
Sure.
I think the project that Dr. Goldman mentioned was the Forest City Ratner project, B2, right?
Yeah.
That one was modular, but it took 5 years to build. And I know this because we were the general contractor who finished it. We weren't on the project initially, but the modular guys that were building it went out of business because it didn't work out. And so when we're pushing these things, there's a lot of details and a lot of things that have to be figured out. And know that, of course, that when you're doing something that's a forerunner or the first adoption or early adoption, that there will be mistakes and lessons learned, right? So. And then, so yeah, that building, I don't know how demountable it is because it's, it ended up having to have a lot of conventional fixes to make it, to get it across the finish line. But again, it was an early adopter, right? So, but there's a lot of great modular solutions out there, and we see them coming in pieces, and a lot of stuff we see out of, London and Australia, and those things, you have to go back to well, what's the purpose of it, right? What efficiencies are you gaining? Are you gaining efficiencies in design or efficiencies in manpower? In Singapore, like you mentioned, Sean, right? The reason they do it in Singapore, right? You have to do these volumetric modular units, right? Is for reduction of labor, right? Is that right? Is that the right way? And so that's that's one context of it, right? But is it overall that is it saving time? Is it actually reducing carbon? I don't know. Back to your last question. So, actually, what was it? Sorry, I was.
Great answer, though, Billy. But no, it was really kind of taking Nikki's riff on the regional move of capital,
yeah,
and then zeroing in on Southeast Asia. Do we think what kind of regulatory approach, or how could we get faster adoption of some things we know would benefit this region?
Well, it's the same as Nikki mentioned, sticks and carrots. You need to have the regulation and you need to have the benefit, right? Just like going back to the stripping of the facades, right? If the government's going to say we're going to strip the facades, while that building's unusable, are they picking up the rent? Are they doing something so that the owner of the building just doesn't have to walk away from the project because it's unusable for a year? You know, and or it becomes an untenable building just sitting there. You know, so there has to be, you know, sticks and carrots, and you know, it does come through government regulation, but it has to have the right intent. It's for the right market. Like the Singapore solution doesn't work everywhere. You know, there's good solutions there for certain reasons, but it has to be something that, and you know, the other side of it is that, you know, like again, Singapore is a good example. They've been trying to do the right thing for a long time. Now it's the volumetric units, right? But before that, it was, you know, precast, right? And you know, that was their solution for a long time. All those HDB buildings with precast walls and columns and half precast slabs. But you know, but again, you know, where was the savings? And so there's regulations that take time to you know, again, it's not a one size fits all. But I think, you know, the right people and the government finding the right solutions for their market, and then, you know, sticks and carrots. Or maybe it's more carrots than sticks. Maybe it's just more tax benefits if you're building efficient buildings. You know.
Yeah.
Good
I
answer.
think I would like to supplement on the
Sure.
the New York one. And I think there's a lot of I mean, for the New York project, basically is there is a contractual issue between the client and the contractor. And basically, it's not a technical issue. And I mean, the design we didn't change. And once it starts, it goes smooth. Another, I can also make another reference, which Hong Kong just finished, and is also a modular building, 18-story high, and it completes in a year, right, in terms of construction. And the design, I think this is, I will agree that it takes a bit longer time than normal because it's the first one in Hong Kong. And in terms of procurement, in terms of government submission and approval, I think it's all new. But now it's used to it, and now Hong Kong now is used to it, and now we're going to have more and more modular buildings, right? And the government, Hong Kong, pretty similar to Singapore, but we are not using strategy. I mean, strategy or policy to force, but we encourage, right? I mean, it's slightly different mentality in compared with Singapore, and we encourage of having a building like if you got a probably something like equivalent to LEED, right? If your building is get a whatever mark, right, you could have a increase in the GFA as a bonus, okay? And also now you go for modular, we will also have another 6% of GFA bonus, right? That we can, you know, to the developer. So we encourage the developer to think of using, you know, be more using off-site fabrication and also modular construction. These are kind of, and also to be green or sustainable, to encourage the building to reduce carbon, etc. And I would see that now. I mean, lots of developer and so forth in Hong Kong and also in China is going to be used off-site fabrication and modular construction. In China, basically, actually that is a regulation of building to be at least 40% to be off-site fabricated, right? So prefabrication or off-site fabrication definitely have a much lower carbon in compared with in situ.
Yep, good one, Dr. Gorman. Now I think, you know, we could probably sit here and talk about this prefabrication topic for a long time, but I think I'll change gears just a little bit. Another one for you, Peter. This one's kind of a fun one. So you moved across the world from China now to the west coast of the USA, and you've seen a lot of different things in your career. Now, you know, if we look back, you know, in time and we see, you know, originally in this whole tall building topic, the US had a lead, you know, with some of the great buildings, Chicago and New York and wider. More recently, the growth has been focused in China. But we know that more recent legislation that the government's tried to cool that off a bit, and put a little more control over architectural expression, height for some cities, which I was very surprised at. But seeing the current environment, from a legislative standpoint and also financially, what do you see the future? Ground zero. That's probably a bad term for the global tall building boom.
Wow. Are you asking regionally or which direction?
You answer as you wish, but yeah, it was more regionally. But I would love to hear some directional topics in there too.
Right. I'm hoping that I think Dr. Coleman said that quoted Rem Koolhaas, right, that this is a never-ending race towards height, and I'm really beginning to. Of course, I respected before, well thought out tall buildings that try to improve the environment and bring positive impact. But I hope that the next generation and future tall buildings are more regionally focused. You were asking how Southeast Asia could adapt some of these topics that we discussed, but I think mass timber is a really interesting material, and I think it has great potential. But some regions don't have the species or the wood that are commonly used. However, I'm recently discovered engineered bamboo product which has similar, or if not strong, higher strengths, and very quickly replenishable. You can grow fields of bamboo in a matter of 6 months to a year, and I think using regional materials, having a goal. So I also support government intervention and incentives, but I'm a little bit against forceful requirements, because different projects, different regions, different countries all have different needs and resources. So as long as we're shooting for net zero or carbon zero, or reducing the carbon every year by 10%, maybe each project can find its own means and methods, and those ways can be shared. And once it becomes standard practice, then it can go into the codes and the regulations. So I'm not sure if I answered.
Yeah, no, that was really great. I think what you say about timber is true. I think the few timber projects we've done here in Asia, you kind of tout, oh, it's sequestering carbon, but then you say, oh, the timber comes from Austria. Makes you think about that. But I love the idea of high-rise timber or high-rise bamboo building. So you're advocating a high-rise bamboo for Southeast Asia. That would be fantastic.
Let's give it a try.
Yeah.
Arab, Turner, and Meinhardt. Let's do it.
Yeah. On the topic, what you said then, Peter, about not forcing legislation, but other ways and means of moving things forwards, and something that we're seeing now, mainly in the UK actually, is consultants undertaking carbon assessment studies as part of their services, and not just for facades, although we are practicing it now in the UK office, and we want to try and roll it out into our international offices as well, but for all trades. And there's developers now in the UK, it's a requisite. So like Lend-Lease, for example, if you don't undertake carbon assessment studies and actually analyze all the materials that you're using and make sure that you're using reduced carbon products, then you don't meet their pre-qualification. So you can't work with them. So this is a great movement that we want to now take out globally. Up to now, it's only our UK office that undertake these formal carbon assessment studies, but it seems to be gaining traction. And if developers require it, then you're going to have to do it. So that's encouraging.
Yeah, Nick,
Sure.
I think you're making a good point. I mean, we're seeing now, I think private sector is moving much faster than the public sector. And many of our clients are now, you kind of say that their C-suite are making these commitments to 2030 net zero, not really understanding how they're going to get there. So it's a interesting challenge and a great opportunity for us to be innovative. So who else wants to pick up where we think the next, what's the next generation for tall buildings globally? Where and how?
I would see that. I mean, yeah, I do a lot of tall buildings. I don't mean that we have to go for taller and taller and taller, right? It's a balance of the demand and supply, right? It should be automatically adjust. And for having like Hong Kong and Shanghai, Beijing, or this kind of like China city, and basically one of the reason is urbanization, where people move from a suburban or countryside to the city in terms of doing their study, university, work, and factory, etc., etc. That drive a demand for buildings, right, and or high-rise building, right, because you want to make the city to be compact and for ease of transportation and so on and so on. And so I will see that, in China, I mean, I'm still I'm working on 3, 500-meter tall tower in China, right? So this limit, yes, I mean, but it doesn't mean it stop, right? The demand is still there. So that's why client is still developing or investing on tall buildings, right? And so if I use this urbanization requirement or the demand requirement, I will still see that, like a city like Ho Chi Minh City and so on still have such a demand, because the people from the various areas moving to like a capital, right, and so forth and so on. And I will see that another one will probably like the Phnom and so forth, right? And this kind of area and will be probably once the demand come up, and probably they will think of a lot of probably high-rise building. But again, besides high-rise building, I mean in terms of government or the city council should also think about the transportation, right? Of having how to work together with all these center, right? And rather than stuck in the traffic and so forth, maybe underground or mass transit will be a solution. And with a mass transit, then they make the energy more efficient, as I said, right? Mm-hmm. And rather than driving a car or maybe a scooter or motorbike, something like that. So I will see coming will be like Ho Chi Minh City and Manila and probably Phnom Penh and Kuala Lumpur, probably one of another city, right? So.
Great points. I think, we're seeing this in a lot of places. People are being a lot more thoughtful. Transport-oriented developments are really where you want to focus on building tall. But something you said, Dr. Gorman, that made me think of placemaking. And you named all these cities which are, globally centers for their region. Do they need their iconic tower? Do they need their twin towers, which did so much for Kuala Lumpur to really put them on the world stage? Do we need a twin tower equivalent in Phnom Penh, Manila, etc.? Who wants to take that one on? Billy, I think you're up.
That's not an easy one, Sean. I mean, it's great when buildings define something in their city, right? I'll give you an example, like the Texaco Financial Tower, right? That became a symbol of pride for Vietnam, right? There was I remember shopping in the grocery store, and there was cheese packets that came with like stickers for like they were inspirational for children, and they had different professions, right? And then one of the profession stickers said architect, and they had a little sticker of the building, I was like, oh, that's our building, you know. And
Oh, that's cool. I thought you were going to say the cheese was actually formed in the shape of the tower.
no, that would have been even nicer. This was the laughing cow circle.
Got it.
But it had the stickers in there, and then so that's something that, you know, they were using to promote. You know, they had other stickers that were doctor and they had a stethoscope, but they had architect and they had that you know, the building, you know, picture. And so there's certainly a certain inspiration that comes from defining buildings, but it can also become too cluttered, right? And so you know, do you have that that one or two buildings that define things, you know, as much as in, you know, so I don't know the answer, Sean. I mean, you know, even New York skyline, right? Once was sort of dominated. You look at all the old TV shows that were based in New York, and they always had the Twin Towers, right?
Yeah.
And then now, you know, you see the new One World Trade Center. It's not as dominating or as distinct as those two amongst the other buildings that have come around it, right? And so it's not as you know, as definable of a skyline as it once was. And likewise for you know, Kuala Lumpur, when there was just the two Petronas Towers, it's like, God, that was, you know, defining, right? But you know, yeah, you know, so I don't know. It's I don't have a good answer for you there. I think it's good if cities can define themselves through some of the things that we contribute to, right? And we like to do that and help define things. But I don't know if it's always the tallest building that they get to there. I mean, you know, it depends the place. It depends what other natural aspects they have going on.
A good answer. Just a quick follow-up. Did you buy the cheese?
Huh?
Did you buy the cheese?
I bought the cheese and I put the sticker on my hard hat.
So look at Burj Khalifa as an example of a big tower.
Oh, Nikki, you froze.
The tower itself, the officers never made any money. They made money from the observation deck and from the sale of what was called Old Town, all of the buildings that surrounded that. And Emaar made huge revenue off that. So much so that when Emaar did the new tower, they haven't even put any floors in it. Yeah, there is no office space there anymore. It's just a structure that leads you straight up to an observation deck at the top, and it's just where do you get the revenue? So you can see that Petronas really put Malaysia on the map, and it made a huge impact in terms of you know, international investment into the country. So as long as these tall towers are bringing in that revenue, and I think that's the same with any building, yeah, as long as it's profitable, it's going to get built. And all of these technologies that we're talking about, they're only going to get used if they're profitable. Because no matter what legislation comes in, if it's a loss, developers aren't going to do it. They'll turn away. So it's all just cash driven.
On what you said, I think it's a great point. You know, when you look at a tall building on its own, it, you know, doesn't have the same positive financial effect as the halo effect that you get from something that has the view of the building. And I wonder, similarly, if we start thinking about, you know, should we view these towers on their carbon merit alone, or there's more of a balanced approach around the effect it has on the wider society or economic circumstances. But Peter, follow up for you. So towers on the bumper sticker, you know, define the city. So how do you feel about the, you know, some of the things that Billy has brought up around the way our cities are starting to develop, like the skyline of London? You know, it's a bit chaotic. Some people love it, some people not so much. So how do you feel about, you know, these cities that start to have these competing architectural objects almost shouting at each other?
Mm-hmm. I wanted to touch on what Nikki was saying about these landmark towers, and I think there should be a distinction between these like national or civic icons, which the Burj Khalifa and the Petronas and the recently, well, currently under construction in Kuala Lumpur, the new second tallest tower.
Yeah.
Right. So I think these are different categories than the developer pushed tall buildings and super tall buildings. So yeah. I think that there should be a distinction, and I think there certainly the investment and return is not the same as other second or third tier tall buildings. So just wanted to lay that out, and you know, I think there should be a distinction. When it comes to skylines, you know, this is something really that naturally occurs, and you know, when I look at Chicago and Manhattan and many other, like London, as you said, you know, these cannot be planned ahead. You know, it's all economics and vision of the landowners, and it's a naturally evolving part of the city, and I think it's really beautiful, and each city has its own unique character. So the more, you know, I think Dubai is very interesting. It's that one is clearly planned, and some may say it's not exciting. Some may say it is more exciting, but I think you know, you provide the rules, and you know, New York City had its own setbacks and maximum heights and air rights. So these kind of regulations that try to improve the urban condition naturally evolved into this skyline, and I think that's a good way to let cities develop and create their own characteristics.
So Peter, good point. So you say that it should be natural, but you also say there should be rules. How much intervention do you think a planning department should have in defining the skyline? Who gets to decide what is the civic, you know, landmark for a building, or should we just let it happen naturally?
Right. Well, that's the tough question, and as I said, you know, the New York City setback laws and air rights laws, these came up because of previous buildings that were too, you know, monstrous, or you know, put you know, a complete shadow over residential houses all day long. So it's a, you know, constantly lesson learned process, and I was really intrigued by Billy's presentation, and just thinking like, wow, you know, why didn't we know that beforehand? But you know, every project is unique and it has its own conditions. So you know, you can't really predict everything in advance, and I think these zoning laws and regulations cannot be, they can't be too limiting, but also they have to be reactive to what has been done. And you know, I slightly, you know, I'm not sure. I haven't decided on the facade changing laws. You know, if it's flammable, it has to be replaced. You know, if it was, you know, code compliant and correct at that time, you know, is it really necessary? Well, for safety reasons, sure. But if it was done correctly and there are ways to mitigate, you know, is that too extreme? So, you know, I go back and forth of how strongly we push these guidelines and regulations. But overall, I think there should be a back and forth. You know, you try to create rules that improve the environment, and within those rules, you know, people will try to push the limit and keep trying new things.
Great. I think we have time for one more question, and I want just a quick lightning round response from all of you, particularly the technical guys. So we talked about rules, and you know, now with the big focus on carbon and you know, really being mindful about the way we use the planet's resources, you know, there's still a really vast difference in the way that we study, define, calculate tall buildings. Some codes in some regions are perceived as being extremely conservative, and that yields what could be seen as a much more higher resource hungry solution than required. Won't name names for regions. I think we all know where they are, but we are seeing some really good work, like people like Cohen Mert at EMAR from the developer side, pushing, you know, local regulators to adopt, you know, just kind of a standard baseline of, you know, using some of the wind tunnel solutions, Nikki, that you suggested by, you know, slightly reducing, you know, wind speeds and using something that's more site specific, you can make a huge savings in carbon, but also financially. So what role do we have as, you know, designers in the industry and, you know, developers and pushing, you know, the regulators toward a common solution that we feel comfortable with, but also gives us a, you know, benefits financially and from a, you know, earth impact standpoint? And maybe we'll go with you, Dr. Gorman, first.
Okay, thank you. I think my to answer your question is no rules. And but of course, I mean, I mean that now I think the for a lot of trade, I would say, we go for performance, right? And use the performance base and to satisfy the requirement, to satisfy the need, and use engineering principle instead of, you know, formula or core practice to fix the root. Because again, core practice are written by a group of people who has experience for their project, which has history already, right? If we are going to face a new challenge or new design and so forth, a new material, so what we can do is use the engineering principle as the foundation, and then use this one to develop the whatever need, and then make the design, the structure to meet the performance in terms of vibration. Because in the chat board, a lot of, you know, candidates are asking about this tall building in seismic, right? And so forth. I mean, make this to a performance, right? Whether we have the set of criteria for various level of performance in seismic, in wind, and also in use, etc. Right? I mean, for me, I use Europe code, I use Chinese code, Hong Kong code, Taiwanese code, Japanese code, whatever code. But basically, it all come from the basic engineering principle, and some of it I have to break through, or I mean, I have to drop the code and use the engineering principle, performance base to prove how it works.
Thanks,
I think this is the way to go.
Great answer. Performance. So maybe just another quick answer, a little bit quicker than that one. Billy, what do you think from a builder standpoint? What's the way forward?
Oh, well, you know, I would say just one thing, just in general, and to kind of follow up on what Gorman said. We need to be careful with complexities, right? And so we're looking at solutions for all of these things, right? And it's more and more features, dynamic features, this and that. But, you know, as Dr. Gorman said, back to the fundamentals, the engineering principles, right? If it's simple to design, it's simple to construct, right? And I kind of worry about this because I see our industry going in two directions, where we have people who are, you know, we're going to like the nth degree in terms of technological advancement, which is awesome. But also, too, I see a lot of common buildings struggling with fundamentals, and some of the forgotten fundamentals in terms of design that then lead to issues as we get into construction, right? And so I think there's a balance to be achieved by maintaining the fundamentals and the past lessons learned over the last 100 years or so, and not repeating those same mistakes, and then coming forward with the same things. But yeah, I think that's the key on the building side is just same as the design side is to maintain the fundamentals, don't forget the lessons learned, and be careful when we get into new technologies, so that those things don't become overly complicated.
Great answer. So performance, fundamentals. Nikki, how about from your standpoint?
Well, from associations with experts, consultant experts and field leaders from contractor sides, if associations can advise governments within their certain regions on setting standards, and minimum standards should be safety and responsibility as these minimum requirements become legislation, then you get a level playing field where you've got a minimum level of quality that everybody's working towards, and you can't go below that. If you don't have that, then you get people undercutting and coming in with subpar products and you're never really going to develop to a point where you're safe. And we can be talking about carbon responsibility being thrown into that as well as a set of minimum requirements. So I think our role as members of associations, along with contractors, are setting this minimum bar and advising authorities on what those regulations should be. And I think it's very important. You've got to be careful that they don't try and create monopolies in doing this, you know, and weed out the little guy so he can't work. It's not something that's supposed to be an exclusive club. But I think it is very critical that these standards are put in place that govern and make sure that there is a certain level that's met everywhere.
Thank you. So we've got performance, fundamentals, governance. Peter, how about for the last word?
All of the above. I think everybody made great points. I'll just give an example. As I'm learning, in California, all new commercial buildings need to meet LEED Silver minimum. So I think that's a good place to start. Of course, I wish it'd be higher. Gold would be even better, but you know, setting a minimum standard and letting projects develop on their own. So you set the vision and goal and see how each project realize. I think that's the way to go.
Great, Peter. So I think, yeah, vision's a good place to pull this to a close. So I think we have a bunch of questions, or from what I understand, Nadia, we were going to open it to the floor. Is that correct?
Yes, that's correct.
All right. So would that be, will you be asking the questions? Sorry.
No, there's no questions from the Q&A.
There's a lot in the chat, though.
Yeah, but the speakers already answered it.
Yeah, multitasking.
Yeah, they are multitasking, Sean.
Okay, sorry, I wasn't keeping my eye on it. So, Nadia, what would you like to do?
So I would like to end this session. Do you want to have maybe a recap?
Sure, a really quick recap. I just want to say, you know, everyone, thank you so much for a fantastic session. We really covered a lot of ground. It was one of the more fun panel sessions I've been involved with. You know, I think we touched on, you know, the future of cities, a lot on technology, you know, adaptive reuse, and, you know, that really big looming question around the climate crisis and carbon really kind of was woven into a lot of our topics, which I think is really appropriate. I also like the way we, you know, we kind of ended the session on, you know, some of the really key buzzwords, you know, was around performance, fundamentals, you know, keep it simple to design, simple to build, governance, and then finally, you know, and probably most importantly, like Peter said, vision. So really great session, and thanks so much. So Nadia, I'll hand it back to you.
Thank you. Thank you to Sean and the rest of the speakers for making time to share your knowledge. Thank you everyone for attending today's webinar. We hope that you find today's webinar useful and informative. But let's not stop here. Let's connect with us on LinkedIn. Once you leave today's webinar, you will receive a survey on the presentation, and we would appreciate if you would complete that and provide your feedback, because we want to do better and we want to do more. So on behalf of Ctbuh and program partners, Turner, Arup, Chancellor, Meinhardt, and Rambol, thank you for joining us today. Stay safe and have a great day ahead. Bye,
Thank
guys.
you all.
Okay.
Thank you,
Bye.
guys.
Thank you, everybody.
Bye.
Bye, guys.
Yeah.